let's give the first talk is actually Sato, Dr. Sato.
Yes.
Luki, yeah, okay. Did I make it? Oh, I needed to actually make it co-host. Okay. Oh, you're co-host. Yeah. Okay. So you can start now. So can you share the screen?
Yes, sure.
Yeah.
So can you see this?
Oh, yeah. That's fine. Good.
I think talk would be 20 minutes or so.
Yeah, you're talking 20 minutes and 5 minutes for question. Total 25 minutes.
Yeah, okay, okay.
Yeah.
Great. So can I start?
Yeah, please go ahead.
Okay. Hello, everyone. First of all, though, thank you very much for giving me a chance to give a talk at this meeting. And I'm pretty happy to be here, actually. And my name is Yuki Sato. I am in Nagoya University in Japan. Okay. And today's topic is about two-dimensional version of the Horava-Lifshitz quantum gravity. And in particular, I wish to study a certain wormholes and baby universes in this context. Okay, and this talk will be based on my recent work with Yanang Bjorn in the Niels Bohr Institute and in the Radboud University in Nijmegen, and also with Yuki Hiraga and Yoshiyasu Ito in Nagoya University in Japan. Okay. Okay. The motivation of this study originated with the following relationship to a certain lattice quantum gravity, namely the two-dimensional causal dynamical triangulations dubbed 2D CDT in stroke is a sort of a lattice regularization for the two-dimensional projectable version of the Horava-Lifshitz quantum gravity. And the projectable version means that the lapse function is just a function of time, as you know. So let me clarify the statements in the following, because this is quite important point in my study. Okay, and in a two-dimensional CDT, we usually discretize the two-dimensional spacetime based on certain kinds of triangles to regularize the ultraviolet divergences that appears in the theory. Okay, and each triangle serves as a cutoff and has the time-like and the space-like edges denoted by the green and blue lines. Okay, and when you discretize the space-time based on these triangles, you have to glue the time-like edge to the time-like edge and the space-like edge to the space-like edge. And in this way, you can have the triangulated two-dimension geometry. And the resulting one has the built-in foliation structures, as you can see from this cartoon. And to quantize this system in the CDT, we have to take the sum over all possible triangulations. So this is the basic philosophy of the CDT. Okay, and in order to extract some physical quantities out of this setup, somehow we have to remove the cutoff. This can be achieved by taking the continuum limit in which each triangle shrinks to a point. So through this continuum limit, the triangulated surface becomes continuous, smooth. Okay, so the point here is that if you take the continuum limit or remove the outer value cutoff, the resulting, as a result, the physics can be well described by the quantum mechanics of the one-dimensional universe whose length is say L, that propagates in time. And this time propagation is generated by H naught. And this H naught is the quantum Hamiltonian of the 2D CDT. Okay. And in fact, this Hamiltonian is exactly equivalent to the quantum Hamiltonian of the two-dimensional projectable Horava-Lifshitz quantum gravity. But here, lambda is the cosmological constant, which should be taken to be positive, because otherwise we cannot take the well-defined continuum limit. So to establish the relationship between the lattice theory and the continuous gravitation theory, the cosmological constant should be positive. So basically, this is the meaning of the statement I gave you. Okay. And in the context of the two-dimensional CDT, we know that we can generalize the situation in such a way as to include the wormhole. So this wormhole is like a handle in the geometry. And also we have the baby universe that vanishes into vacuum. So in the lattice setup, actually you can take in all possible wormholes and baby universes in keeping with the foliation structures. So this is the point. And a somewhat amazing thing is that you can actually take a sum over all possible wormholes and baby universes in a non-perturbative fashion. If you can use some mathematical techniques called the matrix models, but whatever. So if you do that, you can get this quantum Hamiltonian. And actually the last term was missing when there is no wormhole at all. And I think it is amazing that if you include all possible wormholes and baby universes, and those effects appears as the very simple term, GS times L squared. And this GS is the coupling constant for the splitting and the joining interactions of the one-dimensional universe. Okay, so we can say that we can extend the system to include wormholes and baby universes. And the question I wish to address in this talk is that to reproduce this extended quantum Hamiltonian, what kind of interaction should be introduced into the two-dimensional projectable Horava-Lifshitz gravity? This is the question I wish to address. Okay, first, let me review what the two-dimensional projectable Horava-Lifshitz gravity is and its relation to the 2D CDT. Let me start with the 1+1 decomposition of the two-dimensional Lagrangian metric. And in this ADM setup, as you know, you specify the space-like hypersurface in the two-dimensional plane. And this H11 is the induced metric on this spatial hypersurface. Okay. And you also have the time arrows sticking out of this hypersurface, and its projection onto the normal direction and the tangential direction to the hypersurface are quantified by the lapse and the shift functions. And if the theory has the diffeomorphism invariance, and of course, you can change the shape of the hypersurface as you wish. So in this sense, we can say the fluctuation is just a gauge artifact if the theory has the diffeomorphism invariance. If the theory has only the fluctuation preserving diffeomorphism, the structure of the fluctuation is preserved, meaning that the system has the built-in fluctuation structure. And the Horava-Lifshitz gravity is a gravitation theory that is invariant under the fluctuation preserving diffeomorphism, as you know. And in particular, in two-dimensional case, the action is given by this. And I have implicitly chosen the dynamical critical exponent z to be 1. Right. And this lambda tilde is the cosmological constant, and eta is the dimensionless parameter, and this kappa is the dimensionless Newton constant, and this k is the trace of the extrinsic curvature. And here, in particular, we consider the projectable case, namely the loss function is just a function of time. And this is the two-dimensional projectable Horava-Lifshitz gravity. And the physics was extensively studied in the paper by Anton and his collaborators. So if you are interested in, please read this paper. From now, I wish to quantize this system. Before we do that, at the classical level, we solve the momentum constant first. And actually you can do that. And after do that, the physics can be entirely described by the gauge invariant quantities. This L is the invariant length of the one-dimensional universe, and this T is the proper time. An important point here is that this proper time is invariant under the fluctuation preserving diffeomorphism. So this is actually the gauge invariant. So having this statement in mind, in order to quantize the system, it totally makes sense to compute the amplitude of the one-dimensional universe, starting with the length L that propagates in time and end up with the one-dimensional universe with the length L prime, based on the path integral. So technically speaking, to compute this path integral, we gauge fix the Laplace function to be a 1. And also we move on to the Euclidean signature for convenience. Anyway, this S naught is the Euclidean action of this system. Okay, and this lambda is related to the original cosmological constant in the Horava-Lifshitz gravity. And lambda can be anything. It can be positive, negative, and 0. But here, I will take lambda to be positive because in fact, this lambda becomes the cosmological constant of the two-dimensional CDT, which is positive. Okay, and to define this path integral, we have to specify the integral measure. And in fact, there are 3 possibilities depending on the geometry of the one-dimensional universe, which is quantified by the parameter A. So if A is 0, it means that we consider the open one-dimensional universe. And if A is 1, we think about the closed one-dimensional universe. And the last one is a bit tricky, but if A being -1, it means that we put a mark on the one-dimensional universe. So putting a mark on the closed universe is roughly speaking analogous to introducing the coordinates on this system. But anyway, so there are 3 possible definition of the path integral measure. Okay, and you can write down this amplitude in this way. So, and also if you discretize the time step as usual, and you can extract this quantum Hamiltonian. This quantum Hamiltonian has the three possible operator orderings, these three. And actually, these orderings exactly correspond to the three different geometry of the one-dimensional universe. So we have the very precise geometric meaning. And the point is that this Hamiltonian exactly coincides with the CDT Hamiltonian. So by this, we can say that the lattice regularization of the Horava-Lifshitz is a two-dimensional CDT. Okay. So what I have explained so far is that if you quantize the two-dimensional Horava-Lifshitz quantum gravity, you get this quantum Hamiltonian, which is exactly equivalent to the CDT Hamiltonian. Okay, and if you specify the topology of the one-dimensional universe to be closed, and precisely you have this Hamiltonian. And in the lattice setup, we know that we can generalize this situation in such a way as to include wormholes and baby universes. And if you take in all possible effects, and as a result, we can get this extended Hamiltonian. And the difference between these two Hamiltonian is the last term. So all the effects coming from the baby universe and the wormholes disappear as this last term. Okay, and what I wish to find is the classical gravitational action that reproduces this extended Hamiltonian once you quantize the system. Okay, that's I wish to do. And this is the answer. So the first term is nothing but the action of the two-dimensional projectable Horava-Lifshitz gravity, as we have seen before. And the second term is the spatial and the bilocal interactions. And this means that the effective spatial wormhole that connects two different points in the space-time at equal time. So this is exactly the space-like wormhole interaction. So if you quantize this system based on a path integral as before, and we get this quantum Hamiltonian. And this is exactly equivalent to the CDT Hamiltonian, including all wormholes and baby universes in a non-perturbative fashion. And this GS is it's exactly the coupling constant for the bilocal interactions. Okay, but at first sight, you may think this correspondence seem to be weird because this bilocal interaction produces a spatial wormhole. On the other hand, in the CDT picture, our wormhole is not a space-like. But having the explicit relationship between the quantum Hamiltonians, we can conclude that the following thing may happen. So first, this bilocal interaction is effective interaction for the wormholes because so if you integrate out all possible lengths of the wormholes, you can get this bilocal interactions. Okay, so if you start with the space-like wormhole And if you integrate out all possible lengths of the wormholes, and you end up with maybe the in the end, the zero length wormhole might be dominant. So if that's the case, this zero length wormhole can cut the one-dimensional universe into two, and also the two universes can merge into a single one because of this effect. So if that's the case, this is totally consistent with the CDT picture. But we have to prove this statement rigorously, which is my future work. Okay, let me summarize my talk. I have explained that if you quantize two-dimensional projectable Horava-Lifshitz gravity, and its physics is given by this quantum Hamiltonian. And at the level of the discretized setup, we can generalize this in such a way as to include all possible wormholes and baby universes. And if you include all of them, you can get this effective extended Hamiltonian. And all the effects coming from the wormholes disappear as the last term. This is a bit amazing, I think. And we have shown that the classical action, gravitation action that reproduce this Hamiltonian after you quantize it is this action. And its beta is the coupling for the bilocal interaction, which is exactly equivalent to the GS. So, okay, I think it's time. So I will stop here. Thank you very much for listening.
Thank you very much, Ruki. So any question, please? We have a couple of minutes left. I have a quick question, Ruki. So after you take this actually wormhole interaction into account, when you quantize the system, is the wave function singular, or is the actual wave function behaviors well?
Well, I just think about a single universe wave function.
So normally, for example, without including the big universe, you can reduce some kind of harmonic oscillator. Then by purposely choosing the order, you can make the wave function renormalizable. What about when you include the the wormhole? Do you still have this kind of property?
Okay. The wave function of the universe, which is a solution to the Wheeler-DeWitt equation, is not normalizable in this case. And so I have some picture.
Okay.
So this blue curve is the wave function of the universe when you include all possible wormholes. And this can be expressed by a certain Airy function. And this is not normalizable.
I see.
Yeah.
Okay. Thank you.
Thank you.
Yeah. Any other questions, please? Okay, I think perhaps if there are no more questions, let's turn to the next speaker. Thank you very much, Zuki. So next speaker, Dr. Baum. So yeah. I think you are mute, Kazuhara. Can you unmute your? We cannot hear you. Can you unmute your microphone?
Okay.
Oh yeah, no, okay. Yeah,
I'm very sorry.
That's fine.
Okay.
So you can share your screen.
Yes. Is it okay?
Yeah.
Can you okay. Thank you very
no,
much.
Okay.
Okay, thank you very much. First of all, I would like to thank the professor and the one to give us the chance to talk about our recent work. Actually, the first time the Professor One Country invited us on work on Horava-Lifshitz gravity, and then um, the collaborator, Professor Joward, will talk about that one tomorrow. And then also Professor Van Kendry give me the chance to talk about our recent work, and therefore I would like to talk about our work on F-over gravity, dynamical system analysis of Bianchi one spacetimes. So this is a collaboration with Dr. Chakraborty and Professor Sa. The first of all, I would like to shortly review on dark energy and modified gravity theories, including especially the F-over gravity, and then I would like to talk about our recent work on F-over gravity. And the second part. The first part, according to the typology supernovae, we know that it is actually supported that the current expansion of the universe is accelerating. There are two main approaches. The first is the general relativistic approach, which is to introduce the dark energy. And the second is to extend gravity from the general relativity. There's three representative approach of the general relativistic one. The first is the cosmological constant. The second is a scalar field like a quintessence. And the third is a cosmic fluid like a chapter gas. And there are also several extensions of gravitation theories. The first is F over gravity. This is, we concentrate on the F over gravity in this presentations. And recently more active works on the F of T gravity and the Terra parallelism. This is studied by Professor Saradakis and his colleagues here. And also the Horndesk theory, including Gravity gravity and Horava-Lifshitz gravity in this session. I briefly reviewed the F over gravity cosmology. The action is given by these expressions. If F over is exactly R, this is general relativity. And from this action, we can have a gravitational field equation like this. And in the flat, homogeneous, and isotropic universe, we have these Friedman equations, and therefore we have the effective equation of state like this one. For example, if we choose the very prototype model of F of R, like a double parallel case, we obtain the effective equation of state. This one, this is the -2/3 for the case of n is equal to unity here, unity. And this is less than -1/3. Therefore, we have the accelerated expansion of the universe in the late time universe. And this is the evolution of the energy fraction for the exponential gravity case. The horizontal axis showed the reducive, vertical axis showed the matter, the fraction of the cosmological parameters. We can see that along the present time, the dark energy become dominant, and therefore, in this case, we have a cosmic acceleration. There are several conditions for the viable F over gravity: the positivity of the effective gravitational coupling, the stability conditions, and the existence of a matter-dominated stage, and the stability of the late time digital point, and the constraints from the vibration of the equivalence principle. This is called the solar system constraints. There are several models of F over R gravity which satisfies the above viable conditions. The Ussovitsky model, the Stravinsky's model, Tsujikawa's models, and exponential gravity model. Okay, let me move to our recent original work on F over gravity, the dynamical system analysis of Bianchi type 1 spacetimes. In this presentation, we present our dynamical system analysis in terms of a new expansion normalized variables for homogeneous and anisotropic Bianchi type 1 spacetimes in F of our gravity under the presence of anisotropic matter. In this presentation, we demonstrate that the Einstein's equations are reduced to an autonomous 5-dimensional system of ordinary differential equations for new variables. We also make the autonomous system analysis in vacuum for the power law form of F of R, and we show that the dynamics can be solved exactly. In this section, we consider the homogeneous and anisotropic Bianchi times 1 spacetimes in F of R gravity and the presence of anisotropic matter. Now, this is action for this model. Let us take a homogeneous and anisotropic Bianchi type 1 metric like this one. Here, A is the average scale factor, and the beta I, these are characterize the anisotropies of the universe. And then we introduce this relations. The beta plus minus is like this one, and the sigma squared is the total amount of anisotropy and the metric. And here the H is the average Hubble parameter in terms of the average scale factor. In this case, the scale curvatures is given by these expressions, and the energy momentum tensor of an anisotropic barotropic universe, anisotropic barotropic fluid, is given by these expressions. And also we have an isotropic equation state like this one. And we have these relations like this. And then in this setting, we have a set of field equations for H, low, beta plus minus. The first one and the second one are ordinary freedom equations. The third one is an equation for the anisotropy. The fourth is the so-called continuity equations. Here, the delta dot beta dot is given by these expressions. To analyze this set of equations, we introduce the logarithmic time like this one, n. And to examine the set of equations, we in this work we use these dimensionless expansion normalized dynamical variables like this one, the U1, U2, U3, U4 plus minus, and U5. U5 is related to the anisotropic matter. In this case, the first equation, the Friedman equations, the first Friedman equations is given by this form. This is a kind of an energy constraint in this system. And by using these new variables, we can find that the equations second, third, fourth can be related to these 5-dimensional system of autonomous first-order differential equations. This one. Here we introduce the parameter gamma. This is given by these expressions. This parameter is related to the form of f of r. So this is the forms of f of r and the corresponding expressions of gamma. The first is these are the power law form of f of r. We have gamma is delta inverse. Delta is here. A part of the power of f of r. The second is a logarithmic one. The third is exponential gravity case. The fourth is the prototype of f of r gravity, like a double power. This is the most prototype one. The last is the double power law case. For general double power law case. If we choose the A is equal to unity and V is equal to 2, this is the Stravinsky inflation. This is consistent with the Planck result. This one. This figure shows that the horizontal axis shows the tilt of the n, and the vertical axis shows the tensor to scalar ratio. Here is the Stravinsky inflation case. This is consistent with the observations in this case. Then we consider the applications to cosmology. The first, we consider the parallel case and the vacuum. The vacuum means that U5 is exactly the error. In this case, we have these relations in terms of our new variables. And after the analysis, we can see that the two-dimensional phase space spanned by the variables U1 and U4, like this one. That this is the figures of the U1, U4 diagrams. The horizontal axis shows the U1 and the vertical axis shows the U4. This blue line is the invariant line. U1 minus U4 is equal to minus U1. And we can see the flow of the solutions. And here, 0, 0 point. This is a fixed point and a stable one. This figure is the case of the delta is exactly unity. This means that R square inflation, R square case of, and this fixed point 0, 0 is leading to the Dojita solutions. This is stable Dojita solutions. We summarize the results of this figure. The vacuum solutions, this means that U5 is exactly the error in the case of the power law form of F of Brown with U5 is exactly the error exactly solvable. This case, delta is exactly unity. The stable fixed point corresponds to the Dojita solutions is found. This is the solution of Stravinsky inflation, which is consistent with the Planck result. And this result is consistent with the past famous studies, these famous studies. In this work, a kind of the proposal to a systematic way to examine the F over gravity system. In this case, the R is given by this, and therefore, from the energy constraints, we have a very simple differential equations, this one. We can see that in this differential equations, we have only unique solution proportional to R squared. This means that the case of R squared is unique solutions among all vacuum F over theories with respect to the existence of digital solutions with arbitrary Hubble H. And the next, this is the case of delta is 0.1, less than unity. This is a U1, U4 diagram. The horizontal axis shows the U1 and the vertical axis shows the U4. This is the invariant line. U1 minus U4 is equal to minus 1. We have a fixed point here. And we have an attractive and repulsive segment located respectively above the below of the depicted points. And this is a flow of the solutions. Then we have a fixed point, however, this is unstable one. We summarize the consequence from this result. The case of delta is not exactly unity. We have these relations, and therefore the Hubble is given by this expressions. if the delta is positive, this means that the small delta is given by these cases. We have a big X singularity. This is a future time, finite future time singularity. And if the delta is less than the arrow, this means that these cases for small delta, we have the parallel expansions. So therefore, this case, this figure's case, we have the parallel expansions, not the zeta one. And finally, we consider the case of the parallel and under the presence of anisotropic matter. In this case, the U1 is not the arrow. We have a finite U5, finite V5. And then in that case, the corresponding autonomous system is given by these set of equations. Here U4 is U4 plus and plus U4 minus, and U5 is given by these expressions. In this case, we have 4 isolated fixed points. The solution with U4 plus and U4 minus are the arrow, namely the following values for the pair of U1, U3, like this one. After the analysis, we can see that in the case of anisotropic fluid, all isotropic fixed points are unstable. And this means that there is no asymptotically stable isotropic solutions in the presence of anisotropic matter. That this is the case for the parallel form of f of r, but and in addition to this, the parallel form case, we have also examined the exponential gravity case like this one, and we can find that for the case of also the exponential gravity, we obtain the same consequences. This means, namely, that we have no stable fixed isotropic points, and no stable. All of the one are unstable under the presence of anisotropic matter. Okay, let me summarize this presentation. In this presentation, we have analyzed the cosmological solutions for homogeneous and anisotropic Bianchi type 1 spacetimes for gravity under the existence of anisotropic matter. It has been demonstrated that the Einstein's equations can be reduced to an autonomous 5-dimensional system of ordinary differential equations for new variables, which in this presentation we defined newly. By making the autonomous system analysis of the vacuum solutions for the parallel form of f of r, we have shown that the dynamics can be solved exactly, and that only for the case of r squared that there exists a stable digital solutions. This is the solution for the Stravinsky inflations, which is consistent with the Planck results. Okay, let me stop here. Thank you very much.
Okay, thank you for the talk. Yeah, any question, please? Let me see. Yeah. So if you have any question, please raise your hand. Use the reaction so I can see you clearly. Because otherwise, yeah. Okay. Yeah. Good. Philip, go ahead. Philip, can you hear me? Yeah. Okay. So yeah, you are still mute. Can you unmute your microphone?
Sorry, excuse me.
Yeah, I can see your microphone is mute, so you need to unmute. Okay. So well, oh, okay. Okay. Okay, can you hear us?
That one is
Yeah, he's
says he will try later.
Nice.
yeah, he can try later.
you.
Okay. So any question? Any other questions? So Kazuhara,
Yes.
so this actually in your analysis is only your conclusion is actually the last one, the de Sitter attractive solution of de Sitter is only for R square term,
Yes,
right?
exactly.
This is a conclusion.
Yes. Yes. So we only R square case, we have a stable Dojita point.
Okay, I see.
If we have some anisotropic matter, we have no stable fixed points.
I see.
And also, even though there is no anisotropic matter, in the case of other parallel form, like the delta is less than unity, like then we have no stable fixed point leading to the Dojita solution, and therefore our conclusion is that the R square case is the only stable Dojita point.
I see. What about this actually for the information? What about for the model which can explain the dark energy case?
Dark energy case, that's a very important point. Because if the dark energy case, the not R square, the dominant term is the ordinary R. So in this analysis, we have no some clues for the acceleration of the dark energy. In this analysis, we can propose some systematic analysis way to leading the Dojita point.
Okay, thank you.
Thank you very much. That's an important point. That's a crucial point. Thank you very much.
Yeah. Any other question, please?
Perhaps, can you hear me now?
Oh yeah, we can hear you now. Okay, good.
Okay, good. So sorry for this misunderstanding. So I
No,
have
no,
a
no.
question.
Yeah, thank you very much.
So my question is because usually, like, if you use like a Wainwright shoe variables, you get like a circle of equilibrium, right? I mean, the Kasana circle is usually how you parameterize Kasana solutions by a circle. So what happens here? Your variables, they are not they do not show this, or what happened?
Like a Kasana type. So there is some works on the Kasana type vacuum solution, like here. So in this case, they are not the Kasana type one, but we have this is here. You can see. Can you see this one? So I think the model will not the same as the one in the Kasana type solutions work. This is the R square case, and this is the not R square, but the parallel form
So-
of F1.
In this case, all Kasner solutions, they're represented by the origin by one fixed point, 0, 0, 0, or in this case minus 3 half 0.
So this is only 0, 0 case we have a Dojita solution, and not.
I see. Okay.
So only the delta is exactly unity. That's the R square case. Otherwise, we have no fixed stable points which can lead to the Dojita one. Only parallel case. Only parallel. Here is only we have only parallel form, like this one.
I see. Thank you very much.
Thank you very much. That's an important point. Thank you very much.
Okay, I think perhaps the time is over.
Thank you very much, Professor Wang. Thank you
Yeah.
very much.
Next is Dr. Satish Kumar. Yeah. Okay. Satish, can you share your screen with us?
Yes, that one. Okay.
Okay.
Can you see me now? Oh,
Yes.
is my screen seen?
Yeah, we can see you.
Okay,
Yeah.
fantastic. Okay. Good morning, everybody. I think it's from morning for me, and it's different time for you. I will be speaking. First of all, I would like to thank Dr. Wang for the invitation. It's a great honor to speak at the Marcel Grassmann meeting, right? It's a great thing in gravity, so I'm very honored to be speaking. So I'll be talking about singularities, nature of singularities in vector tensor theories of gravity. It's mostly based on my recent papers with my collaborators, Roberto Chan and Maria G. Fatima. And this was published only recently. Okay, so let me give you the summary first, right? So what we do is we study two simple cases, right? Because only in simple cases we can get greater insight into the theory, right? So firstly, I consider the Friedman-Robertson-Walker metric and study all the possible 9 solutions, all the combinations of the k and the lambda. So there are 9 possibilities, and 3 of them seem very special, right? So all of them with k equal to -1 for all 3 possible choices of the cosmological constant. The FRW metric is singular, but it's not the case. The corresponding solutions in general relativity are not singular, and we have verified these solutions using the Raychaudhuri equation for focusing of time-like geodesics. This is the first part. In the second part, we study black holes. There exist only few analytical solutions for a spherically symmetric static metric. In fact, Dr. Wang and his collaborators, his students, have published a paper just like 3 weeks ago. More solutions in Einstein ether theory. We found that there are analytical solutions for this choice of this combination of free parameters C1, 4. For 3 of them, we surveyed everything possible, and for these numbers, for these choices, there exists an analytical solution. So we picked those. Otherwise, there is nothing special about these choices. And we found these solutions have singularities, but they have no horizons, neither killing horizon nor universal horizon, right? Thus, we have naked singularities. So this is the summary of my result, right? So in the FRW case, we have new singularities that don't exist in general relativity. In the Schwarzschild case, we have central singularities, but without horizons. But those horizons do exist in the general relativity case. So okay, so that's my summary. So now I'll start with introduction. Vector tensor theories of gravity, they contain, besides the usual metric, they contain a 4-vector, time-like 4-vector, right? So in some cases, this 4-vector is constrained. In some cases, it's not. So we can classify this as constrained theories and unconstrained theories, right? So among the constrained theories, Einstein ether theory, proposed in 2001 by Jacobson, chronometric theory, which is a low energy limit of Horava-Lifshitz theory, proposed. I did my PhD studying Horava-Lifshitz theory. Chronometric theory is one of the low energy limits, and that can be related to Einstein ether theory. That was showed in 2010 by Jacobson, I guess. And Kostelecki-Samuel theory, perhaps one of the oldest models of vector tensor theories, that's something string inspired. in fact, Einstein ether theory is partly inspired by this theory. Recently, this has a new avatar called Bumblebee Gravity, right? Since 2004 by Kostelecki himself. So these are constraint theories. That means the 4 vector, the ether, what we call ether, is constrained. Whereas in the unconstrained theories, there are 3 of them, right? So the oldest being Will-Northwood theory and Hellings-Northwood. And in 1981, there is a general vector tensor theory. This theory was presented in the first edition of Clifford Will's book, right? So he shows that the other 2 are particular cases of this theory, right? I wanted to go in greater detail about these theories because there exists no good introduction to vector tensor theories, right? So the only book is where they appear as an introduction is in Clifford Will's book, but doesn't have much details. Okay, so here I create the map of these theories, right? So these unconstrained theories, right? So in the constrained theories, the constraint appears as a Lagrangian with the Lagrangian multiplier term. So if you set that equal to 0, we get the unconstrained theories, right? So that's why I am saying Einstein ether theory is the most general theory of most general case of vector tensor theories. And this Kostelecki-Samuel theory happens to be a particular case of Einstein ether theory and chronometric theory too. Whereas this vector tensor theory, general vector tensor theory, has the other 2 has particular cases. But in case of Einstein ether theory, if you set this constraint equal to 0, right? So remove that unit time-like vector constraint on the ether, we would get this, right? So I wanted to do this in more rigorous form than what I'm showing now, but I think for time being, it's good enough, right? So having established Einstein ether theory is a bigger vector tensor theory. So let me give you details about the Einstein ether theory, right? So this is a general covariant model which breaks Lorentz invariance because of the presence of dynamical unit time-like vector, right? So this vector field is not matter, right? So this is dynamical, just like the metric. Okay, and Einstein ether theory is the most general in the following sense. It's diffeomorphism invariant, right? It has the ether vector, right? The vector field, and the field equations are of the second order differential equations, both for the metric and for the ether field, right? So if you try to following these 4 constraints: diffeomorphism invariance, vector field, second order differential equations for metric and for the vector field, you end up with Einstein ether theory, right? So in that sense, it's the most general theory. So kind of I'm justifying my title, right? So, but I wanted to do much more than this. I wanted to show results from all these 6 theories. But for now, it's all right. Okay. So here is the action for the Einstein ether theory, right? So we have the usual Einstein part, that's the general relativity. We have the ether part, which is also dynamical, right? And we have the matter, right? So in today, I will not be considering any matter, right? So it's a vacuum case, both cosmological and black hole, because it's easier to study and we can get greater insights by studying simple cases, right? So here in this action, there are these 4 coupling constants, right? C1, 2, 3, 4. In fact, if I write in the unconstrained theories, there will be another omega term here, which multiplies the Ritchie scale. Right? So lambda is a Lagrange multiplier here, right? So this term would be in the case of unconstrained theories. All right. So do you still see me and hear me? Because my computer said my internet is unstable, but I hope I'm audible, right?
Yeah,
So,
yeah, now it's okay.
in the weak field limit, okay, thank you, Dr. Moore.
That's good.
So this is a coupling constant, right? So G is a coupling, and Gn is the Newtonian constant, right? So here we recover the Newtonian limit when C1 plus C4, right? So which we call C14 is 0, right? Not necessarily individually they are 0, but otherwise also this is the case, right? So, and the Newtonian limit is recovered only when the C14 is less than 2, right? So when it's greater than 2, gravity becomes repulsive, right? So because it becomes negative, that means it becomes repulsive. And when it's 2, this becomes 0. So looking at the coupling constant here, this is in the denominator, right? So the action blows up. So it's just meaningless. So C14 equal to 2 is meaningless case. So C14 less than 2 is a physical case. So we concentrate only on those things. So that's about the formalism, right? So now let's study the initial singularities, right? So for that, we go for the usual, the Friedman, Lemaitre, Robertson, Walker metric, right? So we have this. And for this metric, the appropriate choice of the ether vector. So we have two choices, right? So one, choose the metric, the form of the metric you want to study, and the corresponding form of the ether vector, right? So this is the ether vector. So the rest is simple, right? So here I'm showing we computed the Hubble parameter, the deceleration parameter, studied the usual Friedman-Lemaitre equations and other things, right? And I'm also showing here Raychaudhuri equation because just to confirm that our results are singular, right? So if the Raychaudhuri equation, if the focusing parameter, right? So this one, if it is negative, meaning we have the congruence, we have the focusing of the time like geodesics, but not necessarily it means space-time singularities. It could be caustic singularities, right? But anyway, we show that these are space-time singularities. These are curvature singularities by showing the Kretschmann scalar blows up, and we verify using the as a separate verification, we do the Raychaudhuri equation. Fantastic, right? So these are the details. It's fine. So now for this case, for positive cosmological constant and this spatial curvature being negative, see there are two possible solutions. This B is a scale factor, right? So this is the scale factor. This is normalized. That means we make t equal to t0, we get this as 1, right? So, and the solution exists only for beta plus 2 greater than 0. That's the physical region, right? So, and later, I'm not showing full details. So with these metrics, so if you compute the Kretschmann scalar, it is singular these two times, right? So because we have two possible scale factors, and these are the two possible times at which the scale factor blows up, right? But if you put beta equal to 0, we go back to general relativity. The Kretschmann scalar is finite. In fact, the value is 8 lambda squared over 3, right? So the Kretschmann scalar is constant. It's finite. That means there is no curvature singularity in general relativity. But in the case of Einstein ether theory, we do have, right? So that means it's a new singularity, right? And we show this by studying Raychaudhuri equation. But here, this has something, right? So it depends on what time slice interval you are choosing, right? So then only this term is negative. So this term will be dominant for certain values of t. So then only it is, right? That's something special. So the second case is null cosmological constant, and the spatial curvature is negative, right? So again, the same case, right? So we have these are the scale factors, right? So we have singularities when beta equal to 0 in the corresponding case in general relativity, right? So here it's hard to see. If you just put beta equal to 0, it looks like you have singularity at some certain time, right? So that doesn't do the justice. We have to go back initially and then redo the whole calculation, setting beta equal to 0, and you see the Kretschmann scalar is finite for the corresponding scale factors, whereas for non-zero beta, especially for beta plus 2 equal to greater than 0, right? We have singularities, again, new singularity, right? So the same case goes to negative cosmological constant and the spatial curvature being negative, right? So same case in all the three, right? In all the three cases, see, this is the Raychaudhuri equation is negative here, right? So that guarantees we have the congruence of time-like geodesics, right? So this is the first part of the result, right? So we talked about the initial singularities, and we verified those things. So I showed the same solutions. If you do the same thing in general relativity, the Kretschmann scalar is finite, there is no singularity. But in Einstein theory, we have singularity for the appropriate choice of these free parameters, right? Now we'll study the black hole case. So let's see how much time I have. Okay, so now in the black hole case here, again, we take the simplest metric possible, right? So the most general spherically symmetric static metric, right? Which is Schwarzschild, corresponding Schwarzschild, right? And the appropriate choice of the ether is this one, right? It's only function of R. Okay. So in order to study the horizons, right? Again, in Einstein theory, the usual event horizon may not mean much because we have the superluminal modes, right? So it's appropriate to study the universal horizon, right? So for that, we define both killing vectors so that we can study the killing horizon by taking the largest root of this equation, right? And we have the universal horizon taking the largest root of this equation, right? So there you go. So basically, we have to find the root of these two cases, right? So to find the killing horizon and the universal horizon. Fantastic. So what we did was, I'm not showing so many details here. When we see the solutions, these are notoriously difficult, right? So they have no solution. I mean, they have no analytical solutions. So we looked for place for what all values of C4, C14, there exist some analytical solutions, right? So it so happened for this value of analytical value of C14, we have an analytical solution, right? So for that analytical solution, we have this A and B, the metric parameters, right? So we have the solution, we have the analytical solution, Schwarzschild-like solution in Einstein theory. And we studied the Kretschmann scalar, and it has two singularities, one at the R being 0 and the other at 8 alpha, right? But later this alpha is not appearing here, right? So this appears only in the intermediate steps, and that has to be negative, right? To have the meaningful solutions, because it comes with a square root with negative alpha, right? So it has to be negative to have non-imaginary real solutions. So here the distance cannot be negative. So the only physical singularity is at R equal to 0, right? And at R equal to 0, you can see the Kretschmann scalar blows up, right? So, and we find the universal and using this equation. So the universal horizon and the killing horizon come as the root of these equations. But as you can see, there are no roots. That means we have a singularity and we don't have the horizon, right? So these equations can be confusing. So let me show this graphically here, right? So this red line here is the corresponding solution in general relativity. You can see, right? So this has the 0, right? So at the initial singularity where the curvature scalar blows up. But here you can see it's discontinuous at the horizon. We have chosen one particular value just to make just for the sake of the plot, right? So this is not continuous because there's a coordinate singularity here in the case of general relativity. Whereas in Einstein theory, that blue dashed line, right? So it's smooth. It goes and then becomes 0 there, right? So there is no irregularity here. In fact, there's no horizon, neither killing nor universal. Okay, so and both of them are asymptotically flat, right? So we show that GRR, right? So tends to 1. This tends to 1. The other tends to 0, right? So they're asymptotically flat. Solutions without horizons in the Einstein theory, but with horizons in general relativity, right? So same thing happens for the other choice of C14. Once again, there's nothing special about these things. It would be interesting to know why for these points only in the parameter space. Well, what's special about these points, right? So we don't know. We picked this number because this is permitted by the theory, and for these numbers, for this choice of the parameter, we have the analytical solution, right? So once again, I'm plotting the GRR, right? So it's discontinuous at the horizon in the case of general relativity. In the case of Einstein theory, it's smooth, right? And the curvature blows up at singularity, right? So the Kretschmann scalar blows up at singularity. Same case with C14 being -6, right? So conclusions, right? So we have new singularities, both cosmological and black hole singularities that appear in Einstein theory that are otherwise absent in general relativity, right? So my interest in this thing is, so we have I've been studying singularity theorems in gory details these days, right? So we all know they are true, but I want to understand, get a better understanding. So for example, what is the corresponding mathematical problem? We have the Lorentzian manifold, right? So with the Lorentz signature, it's the Riemannian manifold with the Lorentz signature, right? So because of the causality, we have this thing, right? So how do we prove this mathematically? Forgetting about the whole general relativity stuff, right? So we have these singularity theorems. Now, if we endow this Lorentzian manifold with a vector field, what happens? Do we have new singularities, irrespective of the theory of gravity, right? So this is what I've been trying to understand. It's very complicated problem, right? It's very dry and very mathematical. But fortunately, I have this Einstein theory to play with, right? So these are the results that I have. So I would be happy to answer if you have any questions.
Thank you very much, Satish.
Thank you so much. Thank you, everyone.
Yeah. So any question, please? I have a quick question, Satish.
Please, Dr. Yes.
Yeah, since you consider Ricciardo equations, so this actually you do not have a matter, but you do have a ether field. So now the ether actually, have you studied the energy condition for the effective ether field?
No, because I don't have any. No, we haven't studied. So this is without going to any energy conditions, right? So this is purely a geometrical thing, right? So the Ricciardo equation is purely geometrical. So we just looked into the time-like geodesics. One of the plan was to what you said, but since we don't know the energy conditions in very well in Einstein theory, So I was afraid that I might make a mistake. So maybe I will wait for you to write a paper on this thing so that I can pick up on that. So
Okay.
would the energy conditions, I think they would change in Einstein theory, right? So
Yeah, I think the papers are effectively this Einstein, this ether field will satisfy all the energy conditions.
okay.
Then you have actually the Hawking parameter singular theorem.
Yes.
So this
Yes.
actually that's why you have singularity.
Okay, so maybe we can study that, right? So I was afraid to study the energy conditions all by myself. So maybe we can study that together.
Okay, thank you very much, Satish.
Thank you, Dr. Mohan.
So yeah, I think now the time is over. Let's turn to the next. Next is Dr. Lapis, Philip. Philip, so can you heard us? You need the first
Yes.
line. Oh, okay, good. Yeah.
Can you
So,
hear me?
Yeah,
Okay.
we can hear you. You can share the screen. Okay,
Okay.
good. Yeah.
So can I start?
Yeah, please go ahead.
Okay, great. So of course, first I want to thank Kanjong, first of all, for the invitation. It's very nice to be here. And two comments is, first of all, if I ask weird questions, there are two main reasons, of course. One of you share, which is, I mean, for me, it's almost 6 in the morning. I'm in Brazil as well. But the second reason is, it seems I'm the only mathematician here by training. So, I mean, I feel both honored and if I make weird questions, it's because actually I have no training at all in physics, so I'm showing my ignorance to you all. But this is, since I'm quite ignorant in physics, this is joint work with Klaas Ugla from Sweden and Juliet Hell from Berlin. So what we try to understand in our recent work is pretty much what happens with the BKL picture in terms of Horava-Lifshitz gravity, right? So the dynamics nearby the singularity, I mean, there's the famous saying, you know, of John Wheeler that matter doesn't matter. It should be local somehow, that particles decouple from each other. So we should really study spatially homogeneous models, and they are oscillatory by some means. And what we wanted to do is to see how this BKL picture changed in terms of Horava-Lifshitz. And for sure, we are not the first ones to do that. We just try to give now our take on these matters. So we consider vacuum throughout this talk, and we consider spatially homogeneous models so that we try to investigate oscillations alone. So here I'm going to talk now about the Bianchi models within this Horava-Lifshitz models. So I consider projectable Horava-Lifshitz. So I have a Lorentz metric. My lapse function depends only on time. And then the action, as you all wrote in different manners, so the action is given by some potential term and some kinetics. And I just emphasized that that the kinetics here, we have some lambda coefficient, and then we have all these higher order derivatives in terms of K1, 2, 3, 2, 6. Let me just say that for our purposes, we group these things in different groups. So for example, here we have just this scalar curvature, but then this scalar curvature squared and all these Ricci, they have the same order, so they're going to have the same effect in terms of the dynamics. And similar, so here we have a cotton tensor times a Ricci. This is alone, but then the other two guys, two cotton tensors and R cube, these have the same order, so to say, so they have the same scaling properties. Okay, so let us just recall that GR occurs when lambda equals 1, right? This fixes spatially, this fixes this constant, and K equals -1, so all other constants vanish. And now we want to understand how these different potentials, they affect the Bianchi models and they affect the dynamics nearby singularities. So in the Hamiltonian formulation, we choose this kind of Misner variables. I mean, this is in some sense similar to Misner. Here, usually actually you consider B0. We have a B lambda times some coefficient that depends on lambda. Let me just say that this is to take into account that the coefficient here in terms of these momenta variables, P lambda and P plus and minus is 1. So we rescale things according to this factor here. So that now the kinetics, they are very nice shape. And then the potential now, again, I just split the potential after you normalize the lapse function and so on in terms of these different types of potential. And as I said, so V1, which is R, is by itself, whereas V2 and 3, which are both the square of the scalar curvature, or 2 Ricci, they are together, whereas V4 is alone. You have 1 Cotton and 1 Ricci, and V5 and 6 is whenever you have 2 Cotton tensors or R cubed. These are also together. Okay. So let me say that I'm not going to write the equations for you, but for all these 6 different types of potentials, we can write the ODE using this Hamiltonian formulation, the orthonormal frame approach for the dynamical systems. And for these variables, we actually end up with a 15-dimensional ODE, which then we with 11 constraints. So effectively, we have a 4-dimensional dynamical system. But in terms of these high dimensional dynamics, we try to restrict and see which should be the dominant potentials, so which should be the dominant asymptotic dynamics. And this is given in terms of the moving wall picture, also by Misner, if I'm not mistaken. So we choose now a time variable, which is minus b lambda, so that the singularity is at infinity. And then you have this particle. So Bianchi type 1, it's pretty much a particle moving in some potential in beta plus and minus, right? And then the potentials, they are pretty much steep exponentials, right? You have all these exponential walls, and these are moving in time on different directions, right? So this is how you give this moving wall heuristic picture. And what happens is that towards the singularity, this Bianchi type 1 particle is traveling. Eventually, it hits these walls, right? These exponential walls. You have a bounce law, and then you so you have in a sense, a type 2 transition, and then you continue moving on with a different direction. So for large times, let me just mention that what we get in this heuristic picture is that we have some asymptotically dominant potential, which in some sense is similar to lambda r gravity. So when most of the coefficients are 0, and we just have this lambda coefficient constant. So what happens is that in this picture, these dominant potential, they can then be approximated by type 2 walls. I'm going to give a picture in just a second, but you have these steep exponential walls, which can then be approximated by type 2 walls. Okay, and the important part that we did here in this heuristic picture is that now these walls, they move with certain velocity v, which is between 0 and 1. Okay. So what happens is that now that at least to give you some content what this parameter means. So as I said, I group together, for example, the first potential, which is just the scalar curvature, or scalar curvature with Ricci, 2 Riccis. Then you have these 2 potentials which have the same scaling here, or these 2 guys as well. And what happens is that, for example, lambda r, we have this type of velocity. So the velocity of these walls depends only on lambda, as it should be expected. But then this heuristic picture says that whenever you have large times, certain walls should be dominant, and certain walls should, sort of say, describe the generic dynamics. For example, whenever you have, I had r squared, for example, with the potential, or 2 Riccis, so something like this. So I end up with this type of velocity. And that means that I have this v, which comes from lambda r gravity, over 4. So it doesn't change that much, okay? So we just have a different parameter for all these models. So what we end up is we have a certain model that should describe all these different type of potentials, except then the parameter is going to be different depending on which choice of potentials are non-zero and which are 0, okay? So in this moving wall picture, so I describe now the dominant wall. So as usual, the type 9, you have this almost triangular shape for large times, and type 8, you have this also triangular shape, but the corners are round in 2 of these guys. And what I want to say is that for large times, usually you have a particle, as I was saying, you travel here, you bounce, you have a type 2 bounce, and then you can describe how this bounce law occurs. But the most important part is that these type 9 walls, except at these corners, which should not describe the generic dynamics, except these corners, you can approximate by type 2 walls. So the type 2 walls, for example, here you have one type 2 wall, here you have another type 2 wall, and here another type 2 wall. So you can approximate type 9 and type 8 by type 2 walls, which is similar in some sense to GR. Okay, so let me then just say that for then the dominant model, we can reduce the 15-dimensional ODE to only now a 6-dimensional ODE plus 2 constraints. So again, effectively, we have a 4-dimensional dynamical system. And let me mention that this is quite similar to Wainwright 2 model, so the Bianchi models in Wainwright 2 variables. The only difference we have here is the parameter V. Okay, the parameter V is the only difference, and I forgot to say here that, for example, here you can see that whenever lambda equals 1 in lambda r, so in this first velocity, you simply have V equals well, that's too early in the morning for me, but it should be 1/2. So GR corresponds to 1/2. Okay, and all these different perturbations in lambda pretty much perturbs 1/2 from one side or the other. Now, as I said, the only difference from these Bianchi models to the usual Bianchi models is in GR then is this parameter V, and this parameter V equals 1/2 for GR. Okay, so again, just a few notes on how we proceed to analyze these dynamics. So by the choice of time we had, so the singularity is at plus infinity. So the parameter V equals 1/2 corresponds to GR. And as usual, we try to understand the dynamics into smaller invariant subsets for this ODE. And this is what is done usually in GR as well. So Bianchi type 1 is when all these n variables are 0. Bianchi type 2 when only one of the n variables is non-zero. Type 6 and 7 when 2 of the variables are non-zero, and depending on the sign of these guys, you have either type 6 or 7. And type 8 and 9, you have all 3 n variables non-zero. Again, depending on the sign, you have either type 8 or type 9. And as usual, we want to understand the generic dynamics for type 8 and 9 for all these parameter V. So all these different parameters V correspond to different choices of potential, right? As I said, V equals 1/2, for example, corresponds to GR. Other people, for example, whenever you consider lambda equals 1, let me just make sure I forgot to say that, lambda equals 1, that means that a quadratic r squared type of potential, you have like 1/8 for V, or if you have r cube, you have V equals 0, for example. So what we want to do is try to analyze all these different type of dynamics for all these different type of potentials in a sense, in a unified manner for a single ODE. And similar to GR as well, or even in Horava-Lifshitz, this has been done before. Now, we're not the first one to come up with a type of Kasna map, which is, as I said, the Bau's law, how you get this transition from one type 1 to another. So let me just mention that in the dynamical system, so here you have the Kasna circle. So this is where was born my question before, what happened with this Kasna circle. And then on top of it, you have these hemispheres, which are pretty much type 2 solutions. Type 2 solutions, they are heteroclinics from the circle to the circle. And in order to understand the dynamics, we simply project it down to this. This is a sigma space. So we just project everything to sigma space, and we see how these type 2 transitions are simply lines connecting 2 points of the circle, right? And the point is, for GR even, this auxiliary point, you can simply draw the line from an auxiliary point to these 2 points in order to get the Kasna map. This is how you get the Kasna map in GR, and this is how you get the Kasna map also in our framework for Horava-Lifshitz. So for GR V equals 1/2, you have the 3 tau points here, T2, T3. And then if you want to understand the dynamics or the Kasna map, you simply draw any point P. You draw the line from P to this auxiliary point, and then you end up finding the map. If you increase V now, so for certain choices of potentials, these points, they get closer, so you can think of them like Q1 over V. When V goes to 1, these guys converge to Q1, which is this point over here. So these points are getting closer to the circle. And on the other hand, so you still have a Kasna map in a similar manner. But then when V is less than 1/2, these points, think now when V goes to 0, these points are going to infinity. But still, you still have a Kasna map defined in this case as well, and you can still describe the dynamics in terms of the Kasna map. The only thing I want to say is that the tau points, which are these 3 points, it's unfolded in some sense to a stable fixed points when v is bigger than half, and to unstable fixed points when v is less than half. Okay, so I mean this is the difference for this type of dynamics. Let me just mention that for all parameters v, we can find a chain of period 3, and this again, well, we're not the first one to do that. For example, when v equals 0, you just have this type 2 transitions, which is this equilateral triangle, and this just rotates whenever v increases bit by bit. So you just see this period 3 rotating. And let me just mention that, for example, when v equals 8, 1/8. So for example, whenever you're in this case, for example, Gianni and Kamenschik, they already found this period 3, for example, in their work. Okay, so we're not the first ones even to find these period 3 orbits. So, but now we can give, in a sense, a unified framework for all these type of potentials. And our main, one of the main points, in a sense, is that, well, GR is a bifurcation point. Okay, so GR corresponds to v equals half, and what I can say is that for v less than half, so whenever you have these arcs, the bold arcs, or to say, all points, they have infinite heteroclitic chains. So you can always concatenate type 2 transitions, and they never stop at any point. Okay, so when v equals half, the set of points with infinite chains, it has full measure. So in terms of GR, the chains, they stop if you reach the tau points. Whenever you reach a tau point, then you have a finite chain. Okay. And then if you look at all pre-images of the finite of this finite of this type of the tau points, then you have a set of measure 0. So you have full measure now for infinite chains. And the most surprising, at least mathematically, is that for v bigger than half, the points with infinite chains is a Cantor set. So usually we teach for undergrads that if you start with a line and then you remove the middle third, you have a Cantor set, and then in the limiting procedure, you have a very nice Cantor set. And here we have a similar thing. So we start with the Kazan circle, and then we look at these stable parts, which were the dashed points in the Kazan circle, and we just remove them. And whenever we remove them, you end up with 3 arcs. We look at the pre-images of these dashed arcs, which were the stable sets, the sets that unfold the tau points, and the set that gives you finite chains. So you look at their pre-image, and then you remove them again. And then you look at the pre-image, and then you keep doing this procedure a la Cantor set constructions. So this is quite surprising in some sense, that even though you have stable fixed points, even though you have stable dynamics, and you expect generic stable dynamics, you have a very nice and interesting structure, which is a Cantor set. And moreover, we can say we can say more about the dynamics. Actually, for v less than half, you have multi-value dynamics. So you have a multi-valued Kasna map. For each point, you have 2 images for some points. But this was proven to be chaotic with a student of mine in São Carlos, São Paulo. And then when v equals half, this is known, this is the GR case, this is known to be generically chaotic. And what we can show is that for the Cantor set, we can construct symbolic dynamics. We can conjugate this map to the shift map, which is known in the dynamics community to be chaotic. Okay. And let me mention that one of the students from Berlin that I helped advise, he proved that whenever you perturb v equals half, so whenever you are close somehow to GR, still all periodic chains, they persist. So you can always perturb all these chains like the period 3, but or for any period you can perturb it and they still persist. Okay. And moreover, for the extremal case, let me just recall that v equals 0 corresponds, for example, to a cubic type of potential. Hauke could construct the full dynamics, so he could describe all the dynamics in these 2 extremal cases, so to say. So let me just give you some results on higher Bianchi hierarchy. So type 6 and 7, that's when I said you have one of the ends is 0, the other 2 are non-zero, and depending on the sign of the 2 guys, if they have different signs, you end up with type 6. If they have the same sign, you are in case of type 7. And again, similar, you can just there's some permutation symmetry in these indices. And let me just mention that again, we can locate all the alpha and omega limit sets. I just draw you the picture, and the main point is that we have Lyapunov function that comes from the scaling symmetries, And at least in the picture, when you project to sigma space, you can see that in a sense, type 2 transitions, they are being pushed down in some sets. So the alpha limit sets are here, and the omega limit sets are here. So you can really locate all the asymptotic dynamics in type 6 and 7. And here again, for GR, you have the tau point as the alpha limit set, and the omega limit set is a portion of the circle. Again, as usual, at least mathematically, the most interesting case is V bigger than half. You have a plane here, actually, and in this plane, you have these 2 points, which are this point and this point. You have, again, a PD2 orbit now, so something like this. And depending if you're on type 6 or 7, either you have a new fixed point here in the middle that you rotate and then you converge to this PD2 orbit, or if you are in type 7, then you rotate outside and you blow up and you go to infinity, okay? But again, outside this two-dimensional plane, you're pushed far from it, and then you converge to these portions of the circle. And as I said, so we use Lyapunov functions, but again, even though the Lyapunov functions we give, they are new in some sense, they are very similar to some which were already used in the literature. For example, even in the 70s, like Bogdan-Avlensky and Novikov, they already used similar Lyapunov functions, and more recently, well, at least the words I'm aware of, Alan Brando, Hans Hengstrom, Lars Andersson, they use different in different approaches, similar Lyapunov functions, but not the same. So now let me just mention for the Bianchi type 8 and 9. So what you expect to be the generic dynamics towards singularities is whenever all the ends are non-zero. And similar to GR, we expect the generic dynamics, they should shadow somehow these heteroclinic chains. So concatenations of these type 2 solutions and transitions, okay? Even though we don't have any result, we still expect, again, that the generic dynamics somehow governed by this type of Kasna map for general choices of potentials V for broad ranges of choices for Horava-Lifshitz in a sense. So for the conclusion, let me just mention that again. So what we can prove in a sense, really mathematically, is that, I mean, GR for some reason or another, which is weird enough, it sits in a very special place in all these Horava-Lifshitz models. Okay, so it is a critical case where bifurcation occurs, and the bifurcation is exactly when you have non-generic chaos to generic chaos. So you have generic chaos in you have non-generic chaos in a Cantor set which has measure 0. So genetically you expect it to be to have stable dynamics, whereas for GR then, which is exactly where the bifurcation occurs, you have a generic chaos, and then for V less than half you have that the Kasna map, even though it's a multi-value map, it is chaotic everywhere. So you have this transition from a non-generic to generic chaos. And I mean, as a mathematician, if you ask anybody, like I mean, because of measurement errors, you should not be expected to be at the bifurcation point. I mean, this is the bifurcation point is not expected to be, you know, like something that you can really find in real life, so to say, right? We should expect to be close to it, but not exactly at that point. But anyways, so what we can do and prove is actually that we can describe fully the dynamics of type 1, Bianchi type 1, 2, 6, and 7 dynamics, and we can conjecture what happened for type 8 and 9, again by heuristics, and we can say what can be expected to occur in this case, even though, again, I mean, you guys are the experts, and I'm sure you guys know much more than me in these matters. So that's all I had for today. So thank you very much for the invitation again, and I hope to get some questions or comments or something like this. So thank you very much.
Thank you, Philip. Any question, please? I think we have about 2 minutes left. Yeah. So, Philip, I have a quick question. Now, you consider actually V less than half, equal half the GR, lambda equal 1 case. In order to avoid the ghost, you need perhaps to consider lambda either greater than 1 or less than 3/2, right? So
yeah,
yeah. So my question is, if you just consider this let's say lambda greater than 1 or equal 1 case, because lambda equal 1 is the GR limit. If I just consider that region, is GR the attractive point in your figure or not?
So no, so what happens is that, I mean, lambda equals 1, that was just to exemplify what happens with the parameter v for some of the cases. But as I draw here, I mean, not necessarily lambda has to be equal 1. Okay, so what actually the only assumption we have is that lambda actually is bigger than 1/3. But besides this, I mean, lambda can vary for any value bigger than 1/3 to get our result. So it doesn't really matter which is the choice of lambda you choose. I just chose lambda 1 to say what happens with the parameters for these cases. But in general, you can choose any potential of any higher order, or you can choose any lambda bigger than 1/3. So that's which in a sense covers the one you suggested, right? Which should be v bigger than half.
Okay. So my second quick question is now so in the actual projector case, you have actually also the parity related term, which is the fifth and the third term. Have you studied the effect of those terms to the dynamic system? I think you do not consider the parity related term, right?
So which term? Some of these potentials, you mean?
Yeah, there's actually more terms for the projector case. There's, for example, the term Kij, Rij.
Yeah, sure. I mean, that's why we put the 3 dots here at the end in some sense. So, I mean, we have we did not consider these guys. Okay, so to be fair, that my short answer is we didn't consider these guys. But as I said, what our point in a sense was that for all these 6 different potentials, you end up with a similar ODE. And we expect that different potentials, again, they would have as like a dominant potential. Some of the potentials will be dominant towards the singularity somehow. So even though I agree with you, there are more potentials and we could try to add them, but our heuristic picture suggests that the model we get is pretty much the same. The only difference is probably that the parameter is going to be different. The point is that, which is the whole point of this bottom part of this slide. So depending on if you add more potentials, I would expect to have different parameters. But that's why in our paper we study all parameters value between 0 and 1, which are all the relevant ones. And then I mean, for the different choices of the constants k and so on, and different choices of potentials, then you get some fixed parameter, okay, v for us. But then we study all possible parameters v, because then in our opinion it covers all these possible cases.
Okay, thank you very much, Philip. I think now the time is over. Let's take a 5 minutes, a quick short rest. Then please make sure I come back after 5 minutes. Let's start from next term is 11:15, the actual European time. Okay, thank you guys. Just take a rest for 5 minutes. Satish, are you still there?
Yes, Dr. Wang. How are you?
Yeah, I'm fine. Yeah.
So when are you coming to Rio?
Yeah, I was actually planning to come this summer, but because of pandemic, I think I had to cancel.
I think this is the first time you have not traveled for a long time, right?
Yeah. So I was actually totally trapped here. So now I think I saw from TV the situation in Brazil is getting better.
It was getting better, but now it is staying at 1.2 million number of active cases. It's not going down. It's just staying at 1.2 for nearly 1 month now.
Oh, this is because of the new variety or?
There is new variant also, but the number of cases is fluctuating a lot. So I think it's like the 4th wave or the 5th wave. We are in the 5th wave in Brazil, but India only 2.
Yeah, that's bad. So now what about the vaccination? No,
it has been for example, for all the professors in the universities and schools and all the teachers, So they gave like 15 days ago. So I got my first dose, Pfizer.
Oh, good. Okay. Oh, that's very good.
So I will get my second dose in September.
I see.
I think by November, December, they will vaccinate everybody above 18.
But why you get in September? Normally here after 1 month. So you have.
I got in, this was in July, no, it was in June, right? So I think they have 2 months or something, June, July,
Okay.
August, September. Yeah, I think 3 months gap. I don't know why. So you got both the shots, Dr. Wong.
Yeah, we already got.
Okay, okay.
Take care.
What is the news about Lucas?
Oh, he's good. No, he's actually doing his practice in hospital.
Wow, already practicing.
This is actually second year.
Oh, where in Houston?
So we have to stop here because the time.
Oh, okay, okay. We can't socialize more.
Yeah, let's start again.
But it's very nice to talk to you, Dr. Wong.
Yeah, me too.
Later.
So I think the first talk of our section is Dr. Fu. Fu, are you here?
Yes, can you hear me?
Yeah. Well, I can hear you. So perhaps you can start it right now. I'm sorry, it's 2 minutes late. I will give you back 2 minutes. 3 minutes actually.
So can you see the screen?
Yes.
Okay. All right. Thanks, Dr. Wang. Okay. Good morning, good afternoon, or maybe good night, everyone. Yeah. Firstly, I would like to thank the organizer to invite me to report our recent work on the Horava-Lifshitz gravity in 3+1 dimension covered with anisotropic matter and the possible constraint from GRB 1708-17A. So this talk is based on our work, our recent work, sorry. Okay, maybe. Our recent work, which was collaborated with my colleagues, Dr. Qingwen Tang and my graduate student, Zhang Tao and Donghui Du. So here is the outline. Firstly, I would like to give an introduction to the motivation, and then I will move to the GW 1708-17 and its electromagnetic counterpart. And in the third part, I would like to give some introduction to the constraints on the Horava-Lifshitz gravity. And okay, so the first question is why we need to test the Lorentz violation. It's well known that the singularity will form after gravitational collapse, as discovered by Roger Penrose, who won his Nobel Prize last year. And on the other hand, we also know that general relativity will lose its prediction if we involve singularities of the space-time. Therefore, we need a full quantum theory of gravity. We also know that the group of Lorentz transformation is a scale invariant. However, the considerations of how to combine the concepts of quantum mechanics and gravity indicate that there is a natural scale at which the physics of space-time predicted by the relativity theory breaks down and thus requires modifications. So this natural scale is a so-called Planck scale. Unfortunately, introducing such a constant scale, in some sense, it itself violates the Lorentz invariance because the relativity precludes any invariant length. So therefore, a series of quantum gravity involves some form of discretization of space-time. It may be a barrier is hard to reconcile with the Lorentz invariance. And in addition, from the phenomenologic point of view, we know that our universe is accelerating expansion nowadays. If we look at the Einstein equations, there are, generally speaking, there are two ways to explain this phenomenon. First is we can modify the right-hand side of equation, Einstein equation. We should need some so-called dark energy, which is which will vary the energy conditions, and we also can modify the left-hand side of the equation. This will lead to the so-called modified gravity. One of the acceptable modifications to the general relativity is models with possible range variation, such as the Horava-Lifshitz theory and the Einstein theory. In addition, we also know that the ultra-high energy cosmic rays are originated from the extragalactic sources. When they propagate in the intergalactic space, they interact with CMB photons, which result in energy and flux depletion. In particular, the photomesis process will induce a separation in the spectrum about 3 to 6 times 10 to 19 if, and lead to the well-known GZK cutoff. This limit, however, was challenged by an observation from Japanese team Agasa in 1998. They found that there may be some violation of the GZK cutoff. 10 years later, the high-risk correlation and the other group parallel correlation also confirmed this result in a very high polarization. Actually, just 1 year later, after Agasa published their results, Coleman and Grashow found that if we introduce the Lorentz evaluation into the theory, and we can write down the dispersion relation in this way. Here he just adds an extra term in this way. And they found that even a very small change may lead to the revolve of the GZK cutoff. So let me turn to the GW17, 0817. So this event is the first detection of the binary neutron stars, and it's also the first electromagnetic counterpart. After the gravitational signals, we found that there are also some other electromagnetic signals, such as the gamma ray burst, and also some optical astronomical transient, and so on. So this gravitational wave observation would give us a new insights of physics in both matter and the gravity sectors. In the matter sector, for example, it may be useful in learning the equation of state in neutron star and the properties of gamma ray burst, and also it helps us to discover the kilonova and so on. In the gravity sector, it may help us to test the gravitational theories and also impose some constraint on the modified gravities. So let me discuss more details about this event. Actually, a very short, gamma ray burst was detected after this gravitational wave event. One of the most important discoveries that they found that there is a difference in the arrival time between these the gravitational signals and these GRB signals. In other words, and after around 1.7 seconds after gravitational wave signals, we detected the GRB signals. And also, this delay gives us a constraint on the speed of gravitational waves. If we assume that the GRB was emitted 0 to 10 seconds after the gravitational wave signals, then one can impose a constraint on the speed of the gravitational waves. So if the gravitational wave is faster than the GRB signals, then we can impose the upper bound, and otherwise we can impose the lower bound. So in general relativity, the speed of a gravitational wave is the same as the speed of light. However, in many alternative theories of gravity,
I think perhaps there's some issue with the connection. Okay. Can you hear us, Foy? I cannot hear you, Foy. Can you hear us? Can you hear me?
Yes, we cannot hear him.
Yeah. Okay. I think now he's perhaps he realized we cannot hear him. He's actually working. Okay. Maybe because of the connection. Foy, can you hear us? That's me. I'm gonna. Oh, okay. So, okay. I think he just quit. Maybe he wants to start again. That's okay. So, yeah, he just replied to me. He can't hear me. Can you try again to connect? We cannot. Can you share your screen? Okay, good. We can still not see you, Foy. Okay. Can you try again? Oh. Okay. Perhaps Foy, can you hear us? Okay, I think now he can, perhaps he can hear us. Okay. Foy, what about can you come back later? After yeah, I can hear you. We cannot hear you. Perhaps we can do the following. Yeah, okay. So perhaps I will let Emmanuel to actually present his work. Then after that, you will come back later. Okay, I'm sorry for the connection. Emmanuel, can you start yours? Then we can perhaps wait for later.
Yes. Okay. Yeah.
Yeah.
Can you hear me? Can you hear me and can you see me?
Yeah, I can hear you and see you very well. Thank you. This is Dr. Saradakis. Yeah.
Let
Okay.
me wait a minute. Where is can you see my? Let me close the chat. Can you see
Yeah.
my presentation?
We can see, but not a full screen. Yeah, now it's better. Good. Now it's good.
Okay.
Yeah.
There is a green. Can you see? There is a green rectangular shape.
Yeah, we can see.
But what is this? Anyway.
I don't know. I saw this from your side. Oh, it's not from your side. Yeah.
Let me. Anyway, I think we can do that.
Okay.
I don't know.
Yeah. Go ahead.
Okay. So should I start?
Yeah, please go ahead.
Okay. First of all, I want to thank you, Anzong, for this nice invitation to give the talk in Master Grossman. It's a pity that we cannot be live in Rome and also, discuss and meet each other. But anyway, this is a good alternative that we have due to Zoom. So very briefly, I'm going to present some black hole solutions on Einstein ether gravity, and then we are going to confront them with observations from the Einstein Horizon Telescope of the black hole M87. So the goal is to investigate Einstein ether gravity and try to extract constraints on the parameters of the theory using the black hole shadow observations. And this analysis is based on this recent paper that we did. The main framework of the whole idea is the following, that the shape and the size of a black hole shadow reflects the features of the black hole solution, which is determined by the underlying theory of gravity. So if you study the geometry of the black hole in the vicinity of the black hole, which is visible due to the photon sphere, so what we call the photograph, the picture of the black hole shadow, you can use this observation in order to probe the underlying theory of gravity, and in this particular case, to extract constraints on the Einstein ether quantities, parameters. So, as you know, and as you shared previously, the action of Einstein ether theory is given by this expression where we have the Einstein-Hilbert term and the Einstein ether correction, in which the Lagrangian here is given by this expression where mu is the ether field. Okay, and here we have the Einstein ether parameters, C1, C2, C3, C4. These are the parameters that we are going to investigate. And of course, lambda 0 is a Lagrange multiplier, ensuring that the ether for velocity, this u alpha here, is always time-like. So again, these coupling constants, these parameters, are the parameters of interest. Now, varying the action with respect to the metric and the Einstein ether field, and of course the Lagrange multiplier, gives this field equations. Okay, where this is the energy momentum tensor of Einstein ether gravity, this is the current, and this is this vector A mu. Very good. So we want to study spherically symmetric solutions. So the first thing is to find this solution, to find the black hole solution in this gravitational theory. We are going to consider this metric. So E of R and F of R, these are not standard coordinates. You will see why. And this is the Killing vector. And these are the R-dependent functions. Additionally, we consider the ether vector parameterized by this expression. So alpha and beta of R, of course, are the involved functions. Now, concerning the metric components, at infinity, we assume asymptotically flat space as usual. So at infinity, this parameterization should go to 1, 0, 0, 0. Now, as you know, in cases like that, in Horava-Lifshitz gravity and in Einstein ether gravity, we have branches and types of solutions. So in this case, we have two classes of solutions. The first corresponds to the special choice of the coupling constant C14 equals 0. So we defined the parameter C14 to be the sum of C1 and C4. And we defined another parameter C123, which is the sum of these three parameters. And this here is different than 0. So this is the first solution subclass. These are the metric functions, and these are the Einstein ether vector functions. Okay. Similarly, for the second function, we find for the second solution subclass, we find these functions here. Now, as you can see, both classes reproduce the Schwarzschild solution in the limit when the Einstein ether parameters are 0. This, of course, is a self-consistency test, and this was expected. So now we are going to transform back to the usual coordinates through this coordinate transformation, and in the Eddington-Finkelstein coordinate system, the metric takes a more convenient form. So this E of R is the metric function. And of course, we need to transform the ether field, and this is the transformed ether field. Now, as you all know, in Lorentz violating theories, there is a difficulty in finding black hole solution because of the event horizons. So in Einstein ether gravity, similar to Horava-Lifshitz, of course, due to complexities, we cannot fully find analytically a rotating black hole solution. So only approximately we can do that. And what kind of approximation we are going to use? We are going to use the slow rotation approximation. So in particular, we are going to expand our metric with this kind of expansion. And this expansion parameter epsilon is the perturbative slow rotation parameter. Okay, so we are approximating the rotating solutions in the slow rotation regime. Now, in order to satisfy the asymptotically flat boundary conditions, we assume, of course, that there is no theta dependence in our parameters. And of course, for the first static solution that we found, we can introduce this expression where J here, as usual, is the angular momentum. So this omega that was here contains the information of the angular momentum. And of course, this is convenient in the literature. Instead of the angular momentum, people are using the rotation parameter A, which is the angular momentum divided by mass. So this is the rotation parameter. Of course, A equals 0 means a static black hole. Now, we have the black hole solutions. Okay, the next step is to see the photon orbits around these black hole solutions. Since these black hole solutions contain deviations from general relativity solutions, the photon sphere is going to contain deviations from the general relativity photon sphere. Can you hear me?
Yes, okay.
Okay, very good.
Okay, yeah.
So, this is usually in the literature. in order to study the geodesic structure of the photon orbits, we use the Hamilton-Jacobi equation. So S here is the Jacobi action, and lambda is an affine parameter of the null geodesic. Okay, we are going to focus on the massless photon propagating on these null geodesics. So in this case, the Jacobi action can be expressed in this form, where, as you know, E here is the energy and J the angular momentum on the photon in the direction of the rotation axis. Okay, the photon propagation obeys the following four equations as they obtain from variation of the Jacobi action with respect to the affine parameter. So these are the four equations, and this K here is the separation constant, and these functions R and theta are given by these expressions. So we know the equations determining the orbit of the photon, and as you know from textbooks, as we are doing in a usual way, we investigate these photon trajectories through the introduction of an effective potential, depending only on R. So in our case, the effective potential is given by this expression, where E is the solution of the black hole that we found previously. Now, here we have two important parameters, psi and eta, which are the impact parameters that determine the photon motion. So psi depends on the angular momentum and eta on the separation constant and the energy. So what are we doing with the effective potential? In order to obtain the shape of the black hole shadow, you see, this is what we're trying to do, to find the shape of the photons rotating the black hole, the deformed black hole. We need to find the photon critical circular orbit. And this can be extracted, as you know, from the following conditions, right? So this critical orbit will be where the effective potential will be zero, and this, of course, derivatives here. And we can extract the geometric shape of the shadow, of the black hole shadow, if we know the impact parameters psi and eta that satisfy these equations. So if you put things inside here, we obtain these equations for eta and psi. Now, the solution of this equation gives you the radius of the photon sphere, this RPS, the radius of the photon sphere. And since we have taken the rotation effect into account, this is expected to be between two values. Now, having this, in the slow rotation limit, we can solve this equation and find these impact parameters, psi and eta. And of course, again, I repeat that here E of R corresponds to the two solutions that we found. Now, what is happening is the following. In the vicinity of the black hole, some photons come to us, some photons fall inside the black hole. These photons that cannot escape determine the black hole shadow. So let me proceed with the final quantitative step. In order to determine the shape of the black hole in general, we need the usual two celestial coordinates, x and y. Okay, this determines how deformed is the circle of the black hole shadow. Here, r star and theta 0 are respectively the distance between the observer and the black hole, the distance between us and the black hole, and the inclination angle between the line of sight of the observer and the rotation axis of the black hole. Okay, so the line of sight between us and the black hole and the rotation axis. By applying the geodesic equation that we found, we can express x and y in terms of these impact parameters, psi and eta. So this now, y squared plus x squared, which is given by this expression, where r photon sphere is the radius of this photon sphere. So this is the expression that determines the Einstein-Ether black hole shadow. You see, this is the expression. Inside here, we have the solution of the black hole, and inside the solution, we have the Einstein-Ether parameters, which we want to constrain. Now, the final step, in order to draw the shadow of the black hole, we need to calculate also the event horizon radius. As we said, in general, these solutions have an event horizon. So this is the quantity, and of course, the other interesting quantity is the radius of the photon sphere. Easily, as you know, you can find that the event horizon is given by this expression, so we get 4 results, and these quantities S and delta are determined by the Einstein-Ether parameters. Of course, 2 of them are complex and are neglected, but on the other hand, we observe that the second 2 solutions in this limit give the Schwarzschild background. So this is the branch of solutions that we are interested in. So now we finished our analytical calculations. What we did is we found the black hole solution in Einstein-Ether gravity, where the Einstein-Ether parameters determine deviations from general relativity. We solved for the photon trajectories around the black hole. We found the effective potential, the event horizon, and the radius of the photon sphere. So now we have everything we want in the slow rotation limit, of course. So let us first study the first solution branch that we found. So this is the effective potential as a function of radius for various values of the Einstein-Ether parameter for a fixed rotation parameter. So this is the different effective potential, and this is the difference in the black hole shadow. Okay, so you can see that depending, this is actually the essence of the whole analysis. Depending on the Einstein-Ether parameters, the black hole shape and shadow changes. This is exactly what we want to do. And of course, here you can see the photon sphere, the radius of the photon sphere, and the event horizon. So the fact that the event horizon does not exist, this is R here, does not exist in small r, means that there is a horizon. There is a horizon. So this is for the first solution class. And similarly for the other, the Einstein-Ether type 2 black hole solution, we find this effective potential, and this is the black hole shadow for various values of the parameters. So now we have the shape. How we are going to use the data? So the Einstein Horizon Telescope observed the shadow of the M87 black hole, and they use 3 quantities. The first is the angular size of the shadow, right? The second is the mass of the black hole, and the last one is the distance between Earth and the black hole. So these are the 3 quantities that are being measured by them. Of course, this is the mass of the sun. And now you can merge this information by introducing a single number. So this D M87, which is D times delta over M. And this is a single quantity that quantifies the size of the black hole shadow. Okay, so this is the combination that we are going to confront. So this is the experimental value of this combination. And we have all the information to calculate this in our solutions. So this is this D, as we say, the diameter per unit mass, this D. So these gray regions here are the experimental bounds of the Einstein Horizon Telescope observation. And these lines here are our predictions for the class 1 of black hole solutions. So here you can see this diameter per unit mass in terms of the Einstein ether parameter for fixed rotation parameter. For rotation parameter, taking 4 values, 0, 0.1, 0.3, 2. So as you can see, as the rotation parameter increases, we get outside the observational bounds. So this is a good test that we are talking about a slow rotating black hole. Similarly, here you can see that the diameter per unit mass as a function of the rotation parameter for fixed Einstein ether parameter. Again, as you can see, when the rotation parameter becomes large, we are getting out the experimental bounds. So this tells us that these parameters, the slow rotation parameter is small, and also the Einstein ether parameters are small, are expected. Now here you can see again for the first class of solution in the plane of Einstein ether parameter and rotation parameter, and this is the allow region for a fixed mass. And here you can see now the dependence on mass. So this is mass versus the Einstein ether parameter for two different values of the rotation parameter. So this is 0 rotation parameter, this is 0.2. Okay, so as you can see, our results favor a slow rotating solution, but not static solution. Now, similarly, we can do the same things in the other branch, the black hole 2 branch. Again, this is the diameter per unit mass. The gray region is the observationally restricted region. Here we have two Einstein ether parameters, C14 and C13. Here we fix C13 to 0, and we play with C14 for various rotation parameters. And here, this is as a function of the rotation parameter for various C14 values. So here is the dependence of Einstein ether C14 parameter. And in these plots, we fix C14 parameter and we play with C13 parameter. Again, A is the rotation parameter, and here is this parameter. The result is similar, that we need to be restricted to the slow rotation limit. Similarly, here we investigate the C14 over A and C13 over A, so A is the rotation parameter. So we investigate the contour plots in these planes for fixed black hole mass, 6 billion solar masses. And you can see the obtained allowed regions. And this is the last plot that we investigate here, the contour plots of mass versus these parameters for various cases. Here is for 0 rotation parameter, here is for slow rotation parameter. And as you can see, in all cases, we are in agreement with observations. Of course, C14 and C13 are restricted to very small values. Okay, so let me conclude. So what we did is the following. First, we extracted the black hole solutions for Einstein ether gravity. These solutions have extra terms comparing to general relativity. Now, we have the solutions, slowly rotating black hole solutions. The next step is to calculate the photon trajectories around the solutions. How we did that? We calculate the effective potential, and we calculate the resulting event horizon radius and the radius of the unstable photon sphere. Of course, this physical features are determined by the black hole solution, which in turn is determined by the Einstein ether quantities. Now, we calculate the induced angular size delta, which combines the mass and the distance and leads to a single prediction. But this prediction is given by observations of the Einstein Horizon Telescope. So we had the observationally determined values of this guy here, and we confront it with our predictions. As we saw, Einstein ether black hole solutions are in agreement with these black hole observations, and we obtain the constraints on the Einstein ether quantities, which of course, as expected, they are close to the GR values, to the GR limit. Of course, this was expected. The interesting thing here is the following, that if you are stick to general relativity, you don't have the freedom to play with the rotation. But in modified gravities in general, and in Einstein ether and Horava gravity in particular, you have the freedom to explain the observations of the Einstein Horizon Telescope using different kind of solutions with different rotation features. So this is what I wanted to say. And just to make an announcement, as you probably know, and Onzon knows well, in Corfu in Greece, we are organizing conferences every September. And please be free to visit the pages here and register. These conferences are going to be in a hybrid form. So they are going to be live. But of course, if someone, due to the pandemic, cannot join, he can join electronically. So thank you very much. I finish here.
Thank you very much, Emmanuel. I think the time is over. Perhaps I will leave a question after the end. We have about 15 minutes to discuss all over. So let's call next speaker is actually our graduate students from Mr. Ajis. Ajis, are you there? See?
Yes, I am. Yes.
Yeah. Okay. So can you show us share your
Yes. All right. Can everyone see?
yeah.
Okay.
We can say yeah.
And can you see
Yes.
the cursor? Yeah.
Huh?
Okay, great. I am Siddhajit. I'm a graduate student at the University of Virginia, and I'm studying under Professor Kent Yagi, and we are collaborating with Professor Nico Yunez in University of Illinois for this project. And we are trying to test Horava-Lifshitz gravity using the I love Q relations. So as an introduction, I will discuss I love Q briefly, as well as a couple notable applications of these relations have with strong field gravity. I is the moment of inertia. It describes how fast the star can rotate with a fixed value of angular momentum. Love is the love number. It allows a description of the deformability of a neutron star by a companion. And Q is the quadrupole moment. So the quadrupole moment can inform the star's deviation away from spherical geometry. And these are universal relations in that regardless of the equation of state, we seem to maintain the same relationship between these values. And as an example, I show love and Q here. So these are many different equations of state, and within some percent of error, we get some nice agreement. So this is a good way to study neutron stars. So this allows us to study neutron stars without equation of state, which allows us to study beyond the limits of nuclear physics. And additionally, any measurement of the three gives us information on the other quantity, which allows us to study values that may not be observationally available to us yet. And this acts as a great strong field gravity test in that we can measure I love Q in alternate gravity theories, and based on deviations from GR, we can test GR and constrain values based on observational data if applicable. Next, I wanted to introduce vector tensor theories. I think we've heard quite a bit, so I'll go through this. So GR is a tensor theory, and this is referring to the metric and quantities that are derived from it. So here I've shown an abbreviated form of the action. So first, we'll look at Einstein ether theory, which is related to chronometric gravity. So we will modify the Lagrangian to include a piece that depends on this U, which is how I denote the ether vector. So this is a fundamental vector to the theory. And because of that, this is why we call it vector tensor theory. And this theory comes with 4 coupling constants, C1, C2, C3, C4. So some notable things about Einstein ether theory is that it breaks Lorentz invariance locally, but we can globally define a preferred time direction by defining the ether vector with a Cronin scalar, as I've shown here, approximately. And this will induce a global time direction, which breaks Lorentz invariance much more strongly. And this also eliminates one of the coupling constants, so we can eliminate C1 using this parametrization. And in chronometric theory, to recover GR, we set these coupling constants to 0 in the way that I've formulated them. And the deviation from GR in the equations of motion can be seen from this chronometric stress energy tensor. And when taking the coupling constant to 0, this tensor will vanish. And yeah, so the low energy limit of chronometric theory, or sorry, the low energy limit of Horava-Lifshitz gravity coincides with chronometric theory, which has interesting properties such as UV completion. And it's worth noting that because of this Lorentz invariance, breaking Lorentz invariance, we have to be careful when mixing time and space coordinates. Yeah. So I wanted to talk about current bounds. Using several observations, such as GW 170817, binary pulsars, black holes, Big Bang nucleosynthesis, and other constraints. These are the current bounds on beta and alpha. So they're very stringently constrained. Meanwhile, lambda is not so stringently constrained. So lambda, I think, is currently constrained to around 0.1 or 0.01. So throughout this paper, or throughout this presentation, I will be setting alpha and beta to 0 in order to see what we can observe and whether we can constrain lambda using I love Q. So to measure I love Q, we use a perturbative approach. And I'll introduce the background. So the background spacetime that we will be working with is a non-rotating isolated neutron star spacetime. We additionally assume the star to be a perfect fluid, which informs the form of the stress energy tensor. And after computing the modified field equations, we find that only the chronometric parameter alpha appears in the field equations. So upon taking the limit that we're interested in, the TOV equations, the background equations, coincide with GR. So we have just the GR background. Okay. Next, we're considering a slow rotation perturbation. And here, throughout this presentation, I'll be using epsilon as a bookkeeping parameter to denote the order of perturbation. So the power on epsilon will correspond to the order of the perturbation that I'm working in. To find I, we take this odd parity perturbation, which adds a T-phi component to the metric, and we can note that the contravariant and covariant form of the ether vector remains stationary and axisymmetric. So when I do this, I'm also perturbing the vector, but using this the hypersurface orthogonality and normalization conditions, I end up eliminating most of the perturbation fields. So it ends up being just the usual 100 form in the covariant form. And upon taking the limit that we're interested in, which is alpha and beta going to 0, this does reduce to GR, which means that the moment of inertia calculation is going to end up matching GR. So why does this happen? We can actually see why analytically. So if we examine the equations of motion, we see that lambda couples two terms that are the divergence of the ether vector. So if we take a closer look and note that both the contravariant and covariant form of the ether vector are stationary and axisymmetric, and the fact that the contravariant form only has phi and t components, we see that this divergence of the ether vector field is going to go to 0. So this is why there's no explicit appearance of lambda in the field equations at this order. This is not true at higher order because the contravariant term acquires r and theta terms. So this divergence is not is non-zero at higher orders. So second order in rotation, we use this to calculate the quadrupole moment. I've summarized briefly what this is. So similar to this field I've added in the TT component, we would acquire a similar field in the RR component, theta theta component, phi phi component, as well as the TR component. So this considers even and odd parity perturbation. So we keep the first order term, add a second order correction. And since we're focusing on quadrupolar effects, we set L equal to 2 in the spherical harmonic. And we can use the diagonal field equations as well as the r theta components to find Q. But we find that this, once again, oddly reduces to GR in the limit that we are interested in. But we do find some apparent non-trivial appearance of lambda in the field equations, specifically in the T theta and TR components of the field equations. And they'll couple to fields I will discuss a bit later in the presentation. So for the tidal perturbations, we switch gears from doing a slow rotation. So we now consider a non-rotating star, which is deformed by a companion star. So this is an even parity perturbation, and I denote this with the first order epsilon. And we focus on the electric love number, and we can see that this love number is defined as the negative ratio between the tidal quadrupole value and the electric tidal field E. Similar to before, we get no presence of lambda in the diagonal and r theta field equations, which are the field equations where H0 appears, which is what we use to calculate the love number. So once again, we find that the love number will be will coincide with GR. And we might wonder why this is. So after simplifying the Cronin stress tensor term quite a bit, we find that the only non-zero term when fixing alpha and beta to go to 0 is this. So we're ignoring all terms that are epsilon squared or greater than epsilon squared in order. And we find that the fact that the covariant form of the ether vector only has a t component, and the fact that the divergence of the ether vector still independent of t and phi yields that the only non-zero terms are going to be the tr and t theta terms for lambda to appear in the field equations. So these field equations yield exactly two coupled second order differential equations for two perturbation fields V and H1. These originate as vector perturbations, but they can be transferred to the metric by a coordinate transformation. So yes, and we can solve for V and H1 for a constant density neutron star to see if they can suggest anything, such as a second love number, which has been found in some scalar tensor theories. So to do this, we carry out a post-Minkowskian analysis. To do this, we expand the functions by order of compactness. The ansatz that I use is shown on the right, and it decomposes the functions by order of compactness. And I'm denoting this order by using the script kappa here. And the thetas here are the Heaviside functions. So outside of the star, we assume the energy density and pressure to be 0. And once we have this ansatz, we solve order by order the TOV and the field equations. And in the interior, we impose regularity at r equals 0. In the exterior, we impose regularity as r goes to infinity. And then we match the values at the boundary. So we impose continuity of the function and continuity of the derivative. And when we do this, we actually managed to find that v and h1 go to 0. And just to illustrate this point, I included the first order in PM expansion for these functions. So this is the breakdown of the equation that you would get, and the solutions are presented above. So in the exterior, I've shown these 2 solutions, and then if we match the solutions at the surface of the star, then impose continuity of the functions and the derivatives, then all of the constants of integration end up going to 0. So we can actually see that V and H1 vanish order by order. So to recap, I've shown that using a perturbation in slow rotation and tidal deformation, the field equations constrained by alpha and beta, the field equations in Horava-Lifshitz after constraining alpha and beta to go to 0 lead to a moment of inertia, quadrupole moment, and tidal love number that will coincide with GR. So unfortunately, I love Q cannot be used to test chronometric gravity. And we see that non-trivial experiences of appearances of lambda seem to also vanish, since our preliminary analysis has shown that V and H1, which are the fields that lambda couples to, seem to also vanish. And future directions, it might be interesting to do this kind of analysis for Einstein ether theory to see if Einstein ether theory can be tested by using I love Q. And also we were thinking about doing F modes, because F modes break this time symmetry. So you would no longer have this vanishing of the divergence of the vector field, since now you don't have a stationary vector field using this kind of analysis. And yes, thank you very much to everyone for listening, and thank you very much for the invitation. It's an honor.
Thank you, Siri. Nice talk. So any question, please? Yeah, you just finished 3 minutes early, so we have a little bit, yeah. Any question? I think if you have question, please use the reactions raise hand, or I can see you clear. Yeah. Let's me start with some question, Cindy. You consider always actually hypersurface orthogonal case, which means the ether for velocity always along the time direction, like what you said. But normally, when you consider no spherical case, the ether field cannot be hypersurface orthogonal. This will be true only when the spacetime is spherical symmetric. You can prove the ether for velocity can be written as a gradient of a scalar field or hypersurface orthogonal. So I guess when you consider Einstein ether theory, maybe the first question you would like to consider, the ether field also has a r direction and also theta direction when you consider rotations. Yeah, seems to me imposing UR equals 0 will constrain your theory considerably. For example, if you in Einstein ether theory, if you assume the ether field has only T components, You will not find a black hole solution. There is no black hole solution. So the only black hole solution exists when you have to have a R component, which means the ether is not communing with the coordinate you choose. Yeah. This is actually my first comment. The second comment is even when you consider chronometric gravity, imposing alpha equals 0, beta equals 0, maybe this is too strong condition. Like you said, alpha is less than 10 to minus 15. Beta is less than 10 to minus 5. So if you impose both of them at the same time, you just actually leave only lambda, which is a C2 in Einstein ether theory. Then perhaps you just eliminate lots of physical parameter space. Yeah.
Yeah, I see.
Okay. Okay. Any other question?
Yes, if I may, I would like to ask a couple of questions related to the tidal love numbers.
Okay, yes, go ahead. So I'm glad to see you here, Gregor. I know you was
yeah, good to
traveling.
be here.
Yeah.
So the question is, when you say that the tidal love number, the expression is the same as in GR, you mean, I guess you mean the general expression in terms of compactness and the surface value of the Y function, right?
Yeah, so if the field equations match GR, then I've determined that the tidal love number would match GR. So if there's no parameters for chronometric that appear in the calculation for I love or for the love number, then yeah, that's what I'm basing.
I suspect that for a given equation of state, if you compute K as a function of compactness in GR and in Horava-Lifshitz gravity, the two curves will not coincide. You will obtain two different curves, right?
Okay, I think I see.
Because first you need to find the interior solution and then study the perturbations and compute the tidal love number.
Okay, yeah, I think I see what you're saying. I'm not sure.
For the slowly rotating case, the curve solution is still a very good approximation to Einstein ether theory. Only for the slow rotating case, like Emmanuel consider. If you have high rotation, nobody knows the exact solution. So
for rotating objects.
I'm sorry. Yeah, if you have rotation, there is no exact solution found yet, either in Einstein ether theory or Horava theory. As far as I know, but there's actually slow rotating case.
Yeah, and another question, if I have time.
Yeah, go ahead, please.
This general expression is the same for all multiple, for all angular degrees L, or only for L equals 2? And what about magnetic tidal love numbers? If you can say something, if you can comment on that.
I haven't studied magnetic love numbers personally, but yeah, I believe for L equals 2 and L equals 0 modes, this holds. Yeah.
Okay, thank you very much.
Okay.
May I ask a quick question?
Yeah, go ahead, please.
Yeah, concerning, okay, this goes to everyone, but concerning the quantitative issues. So in the end of the day, if we put down the numbers, is there any hope to see deviations from GR in I love Q expressions and observation concerning the neutron star mergers or the black hole shadow in the near future? Is there any hope to see the effect of Einstein either or Horava-Lifshitz theory in this kind of observations in the near future?
Yeah, I mean, this is what we found is that I love Q most likely cannot be used to test chronometric gravity based on our findings, but there may be other approaches that we can take. I'm not sure yet, though.
Okay, very good.
Yeah, that's a comment after Emmanuel. That's a very good question, Emmanuel. I think if you just look under the metric, I mean the space-time spherical symmetry all with the rotation. Seems to me it's very difficult to find further constraints because you can see the C1 through, for example, already restricted to 10 to minus 15. C14 is 10 to minus 5. So with those kind of things, directly, let's say, this is my personal opinion. Directly observe some shadows. I think perhaps the deviation is very small. But said that recently we have been studying the quasi-normal mode of black holes. There we found perhaps there's some observational effect when we really measure the quasi-normal mode, which can be measured actually within, let's say, in the next generation of detectors. Yeah.
Yes.
Mm-hmm. Okay. Any other question, please?
I have a question for Emmanuel, please.
Okay. For the Emmanuel, can we go later because I also have questions to him. So perhaps we can ask Fuan to finish his
both
work.
Ajit and Emmanuel. It's fantastic work. You are trying to relate these things with the
Fuan, are you
the
there?
observations.
Yes, I'm here. Can you hear me?
Yeah, I'm sorry. Can you? Yeah, can you?
While
Okay,
they're finding, I have one silly point for Sid. Sid, when you go around saying "I love Q," you might get into trouble.
Yeah, I've heard recently. I've heard recently.
Okay, let's actually finish his part.
Okay, can you see?
Yeah, now we can see. Yeah.
Okay. I'm sorry. So maybe let me continue here. Okay.
Emmanuel, my question is about equation 20 in your presentation.
Oh, statistical. Can we just finish?
Oh, sorry. Yes, please. Oh, sorry. Okay.
Then we come back to actual question. Yeah.
Okay, I'm sorry. Okay. Okay, maybe let me continue here. So last time I just talked about that this GW 170817 will impose a constraint on the speed of gravitational waves, and this may help in convert to a constraint on the speed of gravitational wave into constraint on the gravitational theories, such as the quintessence Brown-Dix theory and the fast gravity. Of course, it also will impose the constraint on the Horava-Lifshitz gravity. So they move to the constraint on this theory. So since Horava proposed his interesting theory, there are great progress in the last 10 years. So for example, there are some health extension of the theory. and also the covariantization of this theory, and also many applications, including applications to cosmology and applications to the black holes and thermodynamics, and also the applications to the non-relativistic gauge gravity theory and condensation and so on. As I recommend to all of you.
Have fun. We cannot hear you again. Can you hear us?
We cannot hear you.
Yes.
Okay, good. Yeah, now it's okay. We cannot hear you. Yeah. We can see your mouse is moving, but we cannot hear you. Fuen, can you hear me? Let's wait for him for a while. Yeah, I think perhaps maybe when he tried to show his screens, there's a problem with the connection. Fuen, are you still there? I think perhaps we can do the following. While Fuen trying to come back, we can actually start to ask some questions. Especially Satis, I think you have some questions to Emmanuel.
Yes.
Go ahead. Yeah, go ahead.
Hi, Emmanuel. My question is about the equation 20 in your presentation. You get the ether vector, right? So you find solutions in some other coordinate, and then you do a transformation, right? So you get that. So
yes.
I try to verify if that ether vector is time-like unit vector, but I could not. It is not.
In which coordinates you mean? In
the one with the alpha minus beta over all that thing after the transformation.
Yes,
right?
yes.
So what is wrong?
But you mean in general or for the particular solution class? Because if you take this E and beta that we find in the solutions, I think you do find it. So, I mean, you are trying to show that in general or in...
No, for that particular, exactly what you showed, right? I've also seen this in other papers. So for that metric, for example, in Ding Zai paper, they have this same thing. So if you open the presentation, I can show you.
Should I open it or?
Please, yeah, please open this, yes.
Let me. Can you
exactly,
see now?
Beautiful, right? Yes. So for this 20, right? So the choice of the ether field for that metric 19. So if I do the norm, it's not going to be -1.
But you mean in general, or if you insert here this solution? Wait, if you insert this solution here for alpha and beta and E of R.
That's okay. For exactly what you showed, not in general, just for the values that you showed.
I think if you put this, because this is that's why we constrain to these constraints. So we focus on C1 to 3 equals 0.
That's correct. Yes.
So that's why we choose this. But I think okay, I think we have done this and it's verified. But let me do that again, and I will send you an email just to be
Sure,
sure.
yes. I will send you my calculations. Maybe you can find the error, right? Thank you so much.
Yes, exactly.
Thank you so much.
Very good.
Fun, are you still there? So, perhaps let's continue to discuss until he comes back. I think he can actually come back anytime. Emmanuel, I also have some question about the case. So you consider the two exact solutions. What's happening if you impose all the observational constraints? Then perhaps all the two solutions actually have been ruled out by observations. So if you consider the physical solution, I call physical because all the parameters has to satisfy the constraints. Do you think your result will be changed dramatically? Emmanuel, can you hear me? Oh, hello? Satish, can you hear me?
Yes, Dr. Wang, I can hear you. Yes.
Okay. Emmanuel, can you hear me? You are still mute, Emmanuel. Can you unmute? Okay, I think Emmanuel. Okay, good. Emmanuel, oh, Frank, are you back? Frank, can you hear us? We cannot hear you. Okay, I think perhaps there's still problem with the connection. Any question to anybody? I think Emmanuel cannot hear Emmanuel, can you hear us?
Yes, I can hear you.
Oh, okay, good. So I think the two exact solution has been ruled out by observations. So I wonder what's happening if you consider the physical space, which has not been ruled out. Do you think you will get some significantly deviation from GR?
What do you mean? Sorry, the physical what? What did you say? The physical?
You see, the two exact solutions has been ruled out by observations already, especially after the GW 170817, because C13 has been restricted to 10 to minus 15.
Yes. This is true. I mean, they are not excluded. Just these parameters are very small, and we found exactly the same, that the window is 10 to the minus 15. Okay, then it's a matter of taste whether this means that Einstein ether is still allowed or we are going back to GR. But strictly speaking, I mean, they are constrained to very small values. This is correct.
So you mean this actually even with the current black hole shadow observation, you can restrict it to C14 to 10 to minus 15?
Yes.
Okay. Okay, that's very good. Yeah. Please go ahead. Another question. I think normally we have a maximum 15 minutes to discuss. Later, after 15 minutes, the conference will close. Will actually shut down our link. Any question to anybody? Yeah.
Yeah,
you
can you hear me?
Yeah, we can
Yeah,
hear you. Yeah, okay,
yeah,
you're
yeah,
back. Okay.
Okay,
Can you-
okay.
go ahead,
Okay,
please.
I'm very, very sorry.
That's fine. I think perhaps
Okay.
because of the connection. So not really your fault. Go ahead. Present your
Okay,
result. please.
okay, okay. Okay. I start from this page. Okay. So here's the model we consider.
We cannot see your transparency. Your PPT.
You
one.
cannot see. Okay.
Yeah.
Maybe. So can you see?
No, not yet. This starting. We cannot see. Satish, can you see?
No, I can't see.
Yeah.
Okay. So, can you see this tab?
Not. Seems your side is frozen.
Okay, maybe this time. Can you see?
Not yet.
Me neither. I don't see it.
Oh, it's wrong.
Yeah, we cannot see.
Are you using the browser or you have Zoom already installed?
I use the Zoom, yes. But maybe I can transform to PDF, maybe. I can try.
Yeah, perhaps PDF.
Okay, sorry.
Mm-hmm.
Okay, let me try again.
Good. Okay. Let's try again.
So can you see
no,
me?
okay.
See
Yeah,
this
now we
time?
can see.
Yes,
Yeah.
yes.
Okay. That's good. Okay. So let me continue here.
Mm-hmm.
Okay. Should this one? Okay. So yeah, last time I just talked about this one. Yes, and also we know that most of the discussions previous focus on the Horava-Lifshitz gravity itself. But there's one question is that how the Lorentz violation of the theory affect the Lorentz violation of the matter. So there are some scenarios to construct the general forms of matter that are consistent with the reduced symmetry of the Horava gravity. For example, the symmetry consistence, which in the 2013 by Kimpton and Padilla, and also in 2012 and 2011. Yes, I and my colleagues and also Dr. Wang also had some contributions to this field. And there are also some spectral action approach and also the dimension reduction approach. This is the approach that we are going to talk about. So here's the model. It starts from 4+1 dimensional Horava gravity, which has a Lagrangian like this. And here, the V is a potential term, which is not relevant to our discussion because we are considered the IR limit because the gamma ray burst is the energy of the gamma ray burst is very low compared to the nth scale of the quantum gravity. So after the KK reduction, we can obtain the reduced Hamiltonian of the theory. Here, the phi is described is a scalar field describing the X dimensions, and the AJ are the gauge fields. And we can make linear perturbations around the Minkowski space-time in this way. And then we put all these perturbations into the equations of motion. We can obtain the wave functions for the electromagnetic and also the gravitational waves like this. And we can do the same things to the FLW background, and we can obtain that this formula. One important thing is that we found that the speed of gravitational waves and that is the same. Both of them are proportional to the square root of beta times c. C is a natural, the normal speed of light. From this result, we can see that if we know the speed of that, then one can constrain, impose some constraint on this parameter beta. So how to do this? We know that if the speed of that is energy dependent, then the two photons of energy emitted together from a distant source will arrive with a time delay labeled by delta tau. And using the observable delta tau EH and EI, the distance of a source and some assumptions on the emission properties, we can constrain the Lorentz variation. So this supports there are two photons emitted with energies E1 and E2 emitted at the same time. If the arrival time are different, that means there's a time delay. And this means the speed of the light is possibly is energy dependent. Moselli found that this time delay is proportional to the difference of the energy of these two photons over the energy scale of the quantum gravity.
For you to let you know, the conference can cut our line any moment within 15 minutes. So
okay, so I can,
yeah.
Okay. So we can phenomenologically write down the modified dispersion relation in this way, like this formula. And from this formula, we can calculate the velocity of the photons. And if once we know the time delay, the value of the time delay, then one can decide that we can obtain the scales of the Lorentz variation. So over the past few decades, there are many GRB events that have the time delay. So here is some samples here. So for these samples, we see that we can have a bound on this any scale of the Lorentz variation. It ranges from 10 to 17 to 10 to 20. So use this result, we can apply this result to this GRB 1708-78. Then we can get some possible Lorentz variation effect. So for example, if we impose the most stringent constraint, this result 10 to 20 GV result, then we can get the difference of the velocity is around 10 to minus 19. So from here, we can estimation of the place constraint on the parameter beta in this have this result. So actually, in 2018, there's a work which discussed the constraint on this parameter beta simply by using the data of the GW 1708-70. And they obtained a constraint on this parameter as this one is 10 to minus 15. So our result actually is more stringent than this one. So let me conclude here. Okay. Firstly, we know that testing Lorentz variation is of very important, of particular significance, and gravitational waves and its electromagnetic counterpart provide a new approach in constraining the Lorentz variation. And the gamma ray burst data may place a new and more stringent constraint on Horava-Lifshitz gravity coupled with anisotropic matter. Then the present result we should know is that the present result is only valid for this model, this present Horava-Lifshitz model, which possesses a feature that the velocities of the gravitational waves and the GRBs are the same. And we also need more data and direct observations of the assumed time delay of gamma ray burst events, along with gravitational waves to confirm our results. Okay, thank you for your listening.
Thank you, Feng. I'm sorry for the troubles.
I'm sorry, yes. Okay.
Yeah. Any question, please? Okay, so I have a quick question for you. This actually, you are consider this actually for the ether theory, Einstein ether theory have surface orthogonal, or for the chronometric theory. This actually for the chronometric theory, right? So not for Einstein ether.
Yeah, not for Einstein ether.
So what's happened if you consider Einstein case? Einstein ether case, not a chronometric. They have a different constraint, right?
Yeah. That's a really good question. I think it also may impose some constraint on the parameters of the Einstein ether theory, I think. But maybe later we can discuss this one. Okay, I think it's.
Okay.
Okay.
Yeah, I know here you just consider the Lorentz variation term actually. Yeah. Okay. I see.
So actually, this this constraint comes from the Lorentz variation of the gamma ray burst itself, not from the Lorentz variation of the Horava-Lifshitz gravity. So in this sense, I think it can impose some constraint on the Einstein theory.
Yeah. Here, actually, you consider a high order dispersion relationship. You just modify
yes.
dispersion.
Yeah.
Okay.
Yes.
Okay. Yeah. Thank you. Any question, please? So if there are no question, let's first thank all our speakers again. You can unmute your microphone. So let's thank all our speakers. Then we can continue if you like until the conference actually shut down our link. So let's give a applause to all the speakers. Yeah.
Thank you all.
Thank you guys.
Thank you.
Yeah.
Thank you.
So any questions, we can use this to discuss a little bit. Sometimes difficult to actually get together. Yeah. Philip, do you have any question? Can you hear us?
Me?
Yeah. So I have some questions for you. Especially you can see now people are very interested in the Lorentz Weyl-Lessing case. The terms which is actually Weyl-Lessing either Lorentz symmetry or the parity symmetries. I think in your discussion, you just impose the parity symmetry. So actually, you just throw all the parity Weyl-Lessing term away. I wonder if you pull back those terms, do they have some very different effect to your chaotic behavior? Or you already consider this, you didn't present in your paper? I read your paper quickly. You have a long paper.
Yes, it ended up being a very long paper because so Klaus Hugler is the physicist in our side and I'm the mathematician and we try to put things together. But so to answer your question, I mean, tell me if I get it wrong, okay? But I mean, the point is, if you have more terms, we still believe you have a similar type of behavior, but depending on the parameters that you consider, and the most important one is lambda, you either expect like a generic chaos or generic stable solutions. So it's not, it really depends on which kind of parameter you choose and which kind of potentials you choose more importantly as well. But I agree with you. So, I mean, we only deal with spatially homogeneous and anisotropic, at least, spacetimes. I'm not sure what happens if you not consider symmetry, if you want to consider inhomogeneous singularities. I mean, we haven't explored those, to be honest. I know that there are a lot of results on that already, especially from some of you guys from the audience, but we haven't explored those type of things, yeah.
Mm-hmm. I think lambda term is important, especially when you consider the curvature is very low. But if you go to the normal singularity point, the high order correction should be important. Let's say the fifth order, especially sixth order corrections, like R cube. Yeah. Since you consider
exactly.
Yeah, go ahead.
No, I was just going to say that exactly. So, I mean, it seems to us that the higher order you consider, the more chaotic actually the system is, because your parameter V gets smaller and smaller, and that means more and more chaos, actually. I mean, in some sense, of course. But the smaller the parameter V, and for example, the R cube, for example, we get something which is very, very chaotic, because we have in our case, the parameter which is called V is 0. This is very chaotic.
Mm-hmm. What about the singularity behavior? So if you consider, let's say, high order correction, when you try to go to the singularity, this high order correction does not make any difference. I mean, when this Bianchi type is always you have space-time singularity. So when you go to singularity, what's the roles this high order curvature term play? So they will not make any significant difference?
They were. So what happens is how to obtain the asymptotically dominant dynamical system, or the ODE. Because what happens is that the higher order you consider, all these guys, these different potentials, they affect differently what kind of asymptotical behavior there is. So in order to select, like for example, a parameter V in our case, a unified parameter, in order to select that parameter, you have to know which should be, in a sense, the more dominant potential, in a sense. So for each potential, and depending on which potential you have, we have a different kind of ODE, of dynamical system. So pretty much like that, depending on which kind of potential you choose, we have a specific ODE. So pretty much that's the I mean, the game in a sense is you guys give me the parameters, you observe, you think you can see in observations, and I tell you which kind of ODE in my case we obtain, for example. So this is more or less like the bound, for example, that we saw today, like on C1, C2, C4, and so on. They would constrain also my parameter V, in which sense, like which are the allowable ones, so to say.
Okay. In loop quantum gravity, for example, the singularity, the Big Bang singularity has been resolved generically. So I wonder if you consider high order correction of Horava-Lifshitz theory, do you still have singularity? Or by properly choosing the parameters, can you try to avoid the singularity?
Yeah, so this we haven't pursued. So I mean, we haven't pursued it. We haven't, and I'm not sure what the answer should be, to be honest. I mean, which we also saw today. Like, we only consider the cases where there is a singularity, and then we rescale the variables to get when we write two variables to get the ODs. But I mean, in order to resolve or to avoid the singularity, we haven't explored, and I have no clue, actually, to be honest.
Okay, thank you. Yeah. Okay, I got a message.
But
I think.
Thank you very much, and it's very nice.
Yes, thank you. Dear chairs, the system will close automatically in a few. Okay, so the system will be closed from the conference purpose. Let's stop here. I'm very glad to see you guys. Yeah, I can see lots of old friends and old
everybody.
See you.
Bye.
See you guys.
Bye bye. See you. See you.
Bye. Yeah, see you. Thank you. Yeah.